Laber, laber, laberababa, laberababa, this is a test. J Ja, wie viel Delay haben wir denn? Alles gut. Kein Stress.
we're good to go. So thanks for showing up, and thanks to Jennifer for inviting me to this session. It's good to be back at JuliaCon. So I am head of product development at Pumas AI. Um, and Pumas AI is a company that is sponsoring JuliaCon, I will mention. But we have a software development branch, which I'm heading, and then we have a consultancy branch, which is then using the products we're also developing. Um, my original training is actually not in this space. I am an econometrician, so statistics applied to economics. So that was my original training together with a lot of programming. And I used to be fairly active in the open source community here in Julia. So I did, way back, I did a lot of the work in linear algebra. But that's mostly in the past now. I don't have time for that anymore. Today's topic is stage programming in pharmacometrics, I've called it. I thought it would be interesting to frame the convenience of Julia by looking back at how you approached modeling data in this space that I'm working in the past. And the tool that I'll be describing here is still the main tool. So even though it's an old tool, it's still around. So all the challenges associated with it are still very much faced by the users. So I will not talk too much about our main product, Pumas, which is completely written in Julia for various reasons. It was already presented at JuliaCon, but in 19 in Baltimore. It was also kind of featuring in JuliaCon 22 when Hussein Adawala gave a keynote. Used to be head of pharmacometrics at Moderna, and their vaccine work for the COVID vaccine was done in Pumas. And finally, Pumas will have a lot of similarities with the tool presented in the next talk, so there would also be some overlap. I'll focus mostly on why Julia is a convenient tool for this kind of modeling work. So a little bit just talked about the more recent ways of modeling data in this space. So clinical pharmacology, you could call it, quantitative clinical pharmacology, you could say. And I'll be looking a bit back on the more classical approaches and what led to PUMAS eventually. So the outline is that I'll give the historical context and then the methodological breakthrough that made it possible to consider these models completely differently from how they used to. And then the tool that came out of that innovation, and then how Julia is the more obvious solution for implementing such a tool. And then I'll look ahead if I have time. So recapping, drug concentrations have been known for a long time to be well modeled by the ODs, or most drug concentrations as they time courses of drug concentrations in the body. So that's very old. So if you have a lot of data, you can typically fit a curve with ODs fairly easily and fairly well, again, provided that you have enough data. So these are concentration for a single subject, and you can see there's a good fit. It's a well-known old data set that is shipped with non-mem, which I'm describing here later. So here we have it again. So we have a subject or time profile of concentrations, and we can, with various methods, nonlinear least squares and so forth, fit the data there. We can then look at another subject, and we can see that there are similarities, but there's also differences. We can estimate the clearance and the volume of distribution for the two and see that they are not the same. And we can consider 10 more subjects in this data set, and then we can fit clearance and volume for those. And we can compute an average, a geometric mean of the values, and get what is often called a population fit for these. And that kind of describes, on average, how this drug works in humans. And that goes together with a description of how much does it vary between the subjects. We can compute coefficients of variations for the parameters and thereby describe the drug. That was how you traditionally approach description of or the pharmacokinetic description of drugs, and that worked fairly well provided that you had enough data. Then Louis Scheiner was a very skilled and visionary pharmacologist at the University of California in San Francisco. He was also very well trained, or at least he knew a lot of statistics. And he made the connection that we could actually consider this a mixed model. So that was a very big breakthrough in this space. So he formulated the modeling here as a nonlinear mixed effects model. Thereby, you didn't have to do these individual fits, averaging, and then summarizing the results, which is a stepwise process that doesn't take into or is not kind of doing a joint probability model for all of the data. If you then consider it a nonlinear mixed effects model, you get a lot of power out of that. You get a full specified statistical model and can draw on everything from the statistics world that will give you a well-defined notion of uncertainty, and you'll know exactly how to simulate it in different ways. You can talk about the parameter uncertainty, prediction uncertainty. You can incorporate effects from covariates and so forth without issues. However, there is a cost. The objective function that you're working with is looking roughly like this. So you need to average out these individual effects, and that is not tractable. Generally, you can approximate it in various ways, but it is super costly. You need to optimize over the population parameters. You need to optimize over the individual effects, the random effects per subject, and you need gradients of both, and you need to solve ODEs for each of the subjects for each set of parameter values. So all of these ODEs will be different, right? So although the structure is the same, the parameters will be different. They'll be different between subjects, and they'll be different over time or as you optimize. So you can't share too much. Stiffness properties, so to speak, can be different between subjects. They can be different during the optimization, which makes this fairly computationally intensive. Hence, you need something that is compiled. So there was a tool needed to be developed to really make these models feasible. So they implemented, or they came up with an idea. So that was Stuart Beal, another statistician who could also program at the same university. He collaborated with Louis Scheiner, and they came up with the modeling specification language that then had to be translated into raw Fortran and then compiled and linked into the non-rem library, which provided the machinery, the optimization, and the statistical interpretation of the objective. And they came up with that back in 80 and then was iterated on in the 80s and the 90s. And there's a small example here of the core of the language. You can see it here to the left, how you model clearance volume and the absorption rate constant. You can write an ODE to describe an oral absorption model with first order elimination, and then an error model for proportional error terms. And this pattern of having a model specification language that is then translated into a compiled language and then compiled and then linked has been followed by all other modeling solutions in this space later on. So Monolix, a French competitor, and open source R solution called LMXer, and then Phoenix from Satara. So that means that you have to have a compiler tool chain running, and that is often complicated. There you can see many, I will come to that shortly. There's a separate aspect here, which is the derivatives, because the optimization is gradient based. So you need to compute derivatives all the way through. You could do that with finite differencing and thereby only need to evaluate the objective, but that is noisy and also somewhat costly, and often it's too noisy to actually work. And they realized that and came up with a fairly smart solution, but also super complicated, where they do symbolic differentiation in the modeling language. Then they have a set of models that have closed form solutions with closed form derivatives. And then finally, they had a system to append the ODEs, eventually to compute sensitivities, or alternatively fall back on finite differences. And then you had to assemble all of these to compute derivatives of the objective function. In this setup, it was not feasible with automatic differentiation, although such method existed at the time. So you can see if you search the forums and literature that this comes at a cost, as so many issues with reliable results, different compilers, different compiler settings simply give different results. There's also the development costs. So this is much more recently. One of the engines, the Phoenix engine, had published some papers last year on their efforts to implement automatic differentiation for their C++-based solution, and that has taken them a lot of effort. You can clearly see that from their publications, and they only implemented this for one level of derivatives. What I should mention is, without going into details, that you need either second order or third order derivatives to compute these objectives, and they only managed to get it at one level so far with huge effort. And just to recap, we all know Julia here, but here these same steps that can simply be written as a macro for the model specification that is then expanding into standard Julia constructs and saved in a variable, and then eventually get compiled when you evaluate it. How much time do I have left? Yeah. I'll try to yeah, I'll wrap up. So just similar model in Julia, and then I will wrap up for questions instead of talking more. We all know the benefits of Julia. I just wanted to recap, or not recap, but look ahead. Sorry. So here, I want to emphasize again that there was this big innovation that the data points here could be considered a nonlinear mixed effect model, and that has served this field very well. But there are challenges. The kind of models that are emerging now are much larger, making it quite hard in terms of the OD system. You want to incorporate more mechanistic aspects, makes it really hard to scale this approach. Some aspects of data is growing, not all. The endpoints are still fairly limited, but there are biomarkers that are growing. How should they be fit into this? There's requests for machine learning methods, which is hard to directly fit into it. It might be possible. And finally, there's a question about, can we do something different with the new hardware that is readily available? Should we use different approaches where we can make better utilization of accelerators? But I'll stop here and take questions, if any.
Thank you for your excellent presentation. Are there any questions? Questions to our speaker? Yeah.
Thank you for the good talk. I was wondering, could you elaborate on where does the marginal likelihood come into play? Because you described that it's hard to tackle the marginal likelihood, but it's not a I know that from a Bayesian view, but it's not a Bayesian model that you're training here, you're working with here, right?
No, these are not Bayesian approaches. These are frequency approaches. But in order to estimate the population parameters, you would marginalize out the individual effects, the random effects.
There was another question here.
Yeah, thanks for the talk. Just a really quick question. Maybe you already hinted at it with the slide, but in one sentence, where do you see Puma's AI going in the next 5 years? Is it just that you want to add more machine learning functionality, or is there also other functionality that you are currently working on and, let's say, have a roadmap for the next couple of years? So basically, what's
No,
coming?
we definitely want to incorporate more machine learning, and we already do so. We have what we call deep Pumas, which is incorporating neural network components in these models, and we want to expand on that and try to see how can we kind of expand on Louis Shiner's original vision and then have more flexible components from the machine learning world and add that to the mix essentially, but remain faithful to the original idea. And then there's all other dimensions, right? Making it easier to actually write these models, iterate on these models through language model approaches and such.
Okay, thank you. More questions?
I just a curiosity. I think you had a slide where something like what staging costs.
Yeah.
And then you said that in the Fortran version that you get very big differences regarding which compiler you use and so on.
Yeah.
Why is that, or do you know why that is? Is there because it's You wouldn't expect that, right?
I think I kind of know it from reading it, and it was kind of self-imposed by them that I think they were too quick on using fast math and those kind of unsafe optimizations for floating point operations that gave too much freedom to the different compilers to shuffle things around. And I think they have been more conservative with their floating point operations later on, which has made it more stable across compilers. I think that was the main contributor in the past.
Okay, but that's just a compiler flag. You can just remove that, right? Or,
Come again?
I mean, this would just be a compiler flag. You could probably just remove that in your CMake.
Yes, but usually I think it also depends on how the built-in module has been compiled and so on, right? You're not compiling everything when you build it.
Okay, thanks again. I think we have to go on to the next talk, but we are staying at mixed effects modeling. Our next speaker is Manuel Huth from the Arbeitsgruppe Hasenauer out of Bonn. And he's going to present his package No Limits JL. Exactly, we are done. So the stage is yours.
Yeah, cool. Thanks. Thanks for having me. Thanks for organizing. And thanks, Andreas, for the introduction also to nonlinear mixed effect modeling. So today I'm going to present no limits. So no limits stands for nonlinear mixed effects, right? So I'm going to trying to convince you that we have limits, of course, but we're trying to kind of fill the open gap of an open source tool for nonlinear mixed effect modeling in Julia. So we changed the title a bit, which you might have seen. So the second part now reads, and a kit for building your own estimator. And that's something we have implemented recently. And I think it's quite nice for the community because we have implemented some capabilities that makes it easy for researchers that do method development to implement their method for estimating mixed effects, which is quite complicated, which we have seen due to this intractable integral, right in our package. So you don't have to write all the premises yourself, but you can make use of the things we have implemented for you. So we're going to see a bit about the overview of no limits, then how to build a model. We will use a warfarin model, PK model to see how we can build a model, how we can estimate it, and then we can see how we can implement some neural components within no limits. And then in the end, we will talk a bit about possible contributions. So we have sketches. We have basically seen very similar curves in the previous presentation. So we might have concentrations over time, and you want to model this for different individuals. So these curves vary for the different individuals. So we end up with a problem like this. We have our observations, which we call Yij here, and they're influenced by some random effects, which we don't know, some known covariates, and they're all kind of influenced by this unknown parameter vector feeder. And we want to make inference about this unknown feeder and, if possible, also about this unknown random effects, which then also all leads to this intractable integral. So what we do in No Limits, we also use a macro-based interface. So we give you a model macro, and there you can define very different sources of models that can be reduced form models, nonlinear models, can also be linear models, ODE systems like PKPD systems, hidden Markov models with continuous time, discrete time. You can implement neural models in the form of neural networks using lux.gl or simple chains. Or we have also like splines and soft tree components implemented, which you can then pair with your model. You can also use custom models, so you can define your own model, kind of you define your own distribution in distributions.gl, and then plug this into our interface. And you can kind of combine all of this if you get the math for the model correctly. You then bind your model to data. We use the standard non-mem NL-mixer2-ish kind of data format. So that means you can also define your events in your data frame directly. After you've bind your model to your data, you want to do the inference for your parameters. You can just do one call on this created data model, which is then called the fit model. And we offer a variety of different estimators, which we will go over in one of the upcoming subsections a bit more in detail. And then in the end, after you have fitted your model, you also might want to quantify uncertainty using maybe asymptotics like walled confidence intervals, maybe profile likelihoods, depending on how big your model is and how expensive it is for calculations. That might be a good shot as well. Or you want to maybe do Bayesian uncertainty quantification using MCMC chains, to which we then interface to Turing. So how can we build a model? So we will first sketch the mathematical model. We have some fixed effects, and we have a variance covariance matrix for the random effects defined. So these parameters are also just fixed effects, and we have some standard deviation for the outcome variable. And then we have our random effects. We have 3 of them, and we say, well, this is just a definition, right? So we say they are multivariate log normal distributed. You could also say that they're maybe normally distributed, multivariate normal distributed, and then take the exponent of all of them afterwards. So that's kind of equivalent. And then we parameterize the parameters of this distribution with the fixed effects. And if we want to, we can also use features like weight. So we have some allometric scaling here for the clearance component here. Then we have the ODE dynamics. So it's very similar to what we've previously seen. And for us, the initial state depends also on a covariate, which is the dose, which you can implement directly via the initial state or via a feature via the data frame. And then you have your observational distribution. In this case, it's just a plain normal, no proportional noise, but that would be possible as well. And the blocks we've just seen are very similar in how we define a model in no limits. So we have the model macro in which we have the fixed effects block, and each fixed effects is one specific type. So it might be a real number in this case, where you define a starting value. You can define a prior. You don't have to define a prior. So if you define a prior, this is used for MCMC sampling, for example, if you want to go for fully Bayesian estimation, but it's also used if you want to run a multi-start. We automatically sample from your priors. If you use a method that doesn't require prior, it's just not used. So this is fine. You can also define other parameters like a matrix. So this is a real diagonal matrix, which is then used for the random effects covariance. So this automatically takes the structure of a positive semi-definite matrix. If you want to have the the covariances also be estimated, so not have a diagonal matrix, you can also use a real PSD matrix, for example, in no limits, which is by default parameterized by a Koleski decomposition. This all happens under the hood, but you can also choose other parameterizations, for example, the matrix exponential. So for the error of the outcome or the standard deviation of the outcome error, we use also a real number in this case, which is scaled here via the log argument. So saying we estimate here on log scale. So it's very similar to this Koleski decomposition we could use for a PSD matrix. We then define covariates. T usually is the time index. You can use other indices for time if you're working, maybe if your time domain is actually a spatial domain. So maybe you're coming from a different field and you're not modeling over time, but over some whatever spatial distance. You could also, you don't have to use T. And then we define a constant covariate on a certain ID or a certain column name. In our case, this is ID. Why we differentiate between these features is because you can use them in different blocks. So a constant covariate can be used, for example, to parameterize random effects because we know it's constant within an individual. So it's going to be constant over the ODE, right? So you can use it to calculate things before the ODE, for example. And you can also use them for the initial conditions of the ODE because you know they're constant over the time course of the ODE. We have something that is called dynamic covariates, which are not shown here, and they're kind of interpolating functions, and you can use them also within the ODE for using covariates. Then how we define the random effects is basically in the random effects block, where we give the random effect a name. In this case here, it's very similar to the math we've seen before. We use a multivariate log normal. We parameterize its mean vector, and we use its variance covariance matrix here then, which we have defined in the fixed effects block omega here. We then also specify the column. So in principle, it's also possible to have like nested random effects, which is, I think, not so common in pharmacometrics, but in theory, it's possible and it's used in other fields quite heavily, especially when you have closed form models without an ODE. So as you can see here, this kind of writes like code, and this is kind of the idea. So you can also include like other components here. If you define a neural network, which we will see later, that only takes like constant covariates as input, you could also use this here to have like maybe learn the relationship of weight on the mean of this multivariate log normal. There you're very free. And it's kind of the idea of no limits, like give you a lot of freedom to define your models and maybe explore new ideas with this. We could have also defined univariate random effects. just like this because we use a diagonal multivariate log normal distribution. It's the same as defining the univariate distributions. For speed, if you know your distribution is going to be independent anyways, then it makes sense if you define the univariate ones because the multivariate ones in the back, they have to create vectors and matrices all the time. These univariate ones, they don't. But for the multivariate ones, it's much easier to switch if you want to include covariances afterwards because you just have to adjust the matrix type you have in the parameter definition. After this, we have a pre-differential equation block, which we just use for renaming here. So we assign to the name Ka just the first random effect, right? So we have defined the random effect as Bi here. And we can go to the first entry of this vector. It's a three-dimensional vector. And when we basically just call it Ka, and we can use this subsequently in all other coming macros. You can use this for calculations. For example, if you define your random effects as normals and you want to use the exponential to then transform them, that's also possible and is done quite often. After this, you define your differential equation just in a differential equations block. So you define what is the derivative on the left side and on the right, just the ODE. So nothing fancy. And then in the initial differential equation block, you can define your initial values for the ODE. You can reuse all constant covariates, fixed effects, random effects, and basically everything that is kind of time constant within here. And it also writes like code, so you can have like longer blocks as we have here for this kind of term here as well. And then in the formulas block, you kind of define your outcome distribution. Here we have a normal distribution that has mean center t. Center is the quantity or the state that comes from the ODE, and this is kind of a function, so you can use it like a function. You evaluate it at time t for the observation that has time t, but you could also use t minus 1, t plus 1, because it's a function. You could even kind of use whatever function in Julia that computes an integral. You could even take the integral over it, depending on your use case, so you're very flexible in how you use these functions. And then we use the fixed effect standard deviation to parameterize this normal distribution. You can also write a lot of things here. Transformations of your states, of your ODE states, fixed effects, random effects, whatever you want. And everything that is picked up or like this as a distribution with this S distributed S tilde will be automatically seen as a distribution by no limits. So you can also have like multiple observables here, which you can define quite straightforwardly. We have used normals here and log normals. In theory or programmatically, you can use kind of all distributions from distributions.gl. In theory, because I told this to my colleague and then he used the Cauchy distribution for this. And who has heard about the Cauchy distribution? Yeah, and the problem, it has a non-finite first moment, right? So all the math behind it breaks down. So programmatically it works, but your estimate is going to be horrible because the theory behind it is just wrong. So you can't use all distributions from distributions.gl. But if you know what you're doing, you're very flexible in what you're doing. You can also define your own distribution, for example. And when I was scanning through the schedule of the JuliaCon, I saw that there's copulas.gl, and I saw then that they are building like also on distributions.gl. So I just tried it out of curiosity. What happens if I put a copula they create just into as a random effect, and for Laplace and Foki, it just worked out of the box, right? I haven't really tested whether this makes sense methodologically. I think from theory, but it's a multivariate distribution somehow, just very flexible, so it should. For SAM and MCEM, we have to do some tweaks to make it work, but that was really nice to see that it kind of worked just out of the box. Okay, after creating our model, we want to fit our parameters, right? So we kind of have these 4 different broad categories, I'd say. Here we have the integral again, to which we group our estimation methods. We have Laplace and Foki here, which are then both based on the Laplace approximation. We have Gauss-Hermite quadrature, but it's more experimental, and this is not adaptive. So it is kind of, if you have a really good prior or your prior is very close to your posterior of the random effects, this might work. Otherwise, yeah, it's a more experimental approach. We have the expectation maximization based algorithms, MCEM, SAEM. We have a fully Bayesian approach, MCMC, interfacing to Turing.gl, and we have plugin estimators, pooled and pooled map. So where we basically fix the random effects at their mean of the prior, and then we do just ordinary estimation, given as we had the true random effects. So what is important here is that it's just all the same function call, and you can exchange the estimator just by using another struct. So if you use Laplace, you can just replace it with FOCI or MCEM or SAEM just with one struct change. And all of these structs, they carry a lot of options. So we have some here for the MCEM. So you can choose your sampler, you can choose the maximum number of iterations, you can choose how many evaluations you want to make or how many samples you want per iteration. And this is just a subset. So this MH is just a Metropolis Hastings, which then interfaces to Turing as well, just a subset. For every numerical optimization, we interface to optimization.gl, for example. So you can choose, I wouldn't say all of them because we only tested basically the optim ones, NLOpt, Blackbox Optim, and optimizers.gl. So you can also use Atom and whatever you like from the package. And it's kind of the philosophy. So we always interface to existing Julia packages when possible, such that we give the user the opportunity to use all the options from these packages. Usually, when we do such optimizations, we might have priors about the starting values, but we don't know the exact starting values. So what we want to do is we want to explore maybe a space of starting values, and we can do this by a multi-start. We can then basically just define in no limits how many draws we want to make from specified distributions. This can be the priors, for example, you have specified, but you can also define the distributions in here with a dict or a name tuple. And then we draw 100 starts, evaluate them, and then take the 50 best and start from the 50 best, just optimization runs. The sampling is by default done by Latin hypercube sampling. So we kind of divide our space into in a grid and draw 1 point from each grid point. Or you can also just draw fully randomly. That's also feasible. And because we wanted to have this just very easy for users, it's basically the same call, but instead of just saying fit model DM MCEM, you just put the multi-start object in front of it, and it does the multi-start for you automatically. So nothing you have to deal about after defining the multi-start struct. So when we started to develop this, so this is a very simplified schematic of the estimators, the deterministic ones, EM-based, Bayesian ones, of the core equations of them. We realized most of them take basically two ingredients, which is here in orange, the complete data likelihood, and in blue, the conditional distribution of the random effect, so which you have to sample, usually using Markov chain Monte Carlo methods. So we thought, well, if current estimators have this, it's probably the case that future estimators are composed of them as well. So what we wanted to do is we want to have like a public API people can use to build their own estimators quite easily, and they don't have to implement all the sampling and the complete data likelihood themselves, but they can care about maybe new statistical properties of their estimators. So this is an example of how you can implement the MCEM with the public primitives we have developed. So you just define a structure that is a substructure of the fitting method. And this takes some fields, can be more like number of iterations and number of draws of the method. And then we define a convenience constructor for it. And then you define a function, which is basically your fitting function, which is a no limits fit method, which takes the data model as input, then a specific type, random number generators, and other keyword arguments you want to. And then basically we won't go through the function completely, but you can use our provided functions to extract the initial parameters from this, from the data model. You can start your fitting loop here for the MCEM, like it's an iterative algorithm. You can sample the conditional random effects here, and then you can use them. Like after the sampling, there comes a numerical estimation step, which we have here. And then we can basically wrap all this in a fit result. And you can then use this new estimator here just as any other no limits estimator. The MCEM is a particularly easy one because you don't have to deal with the nested gradient, which comes all from the nested optimization in the gradient as in Laplace or FOCI. So this writes quite shortly. But I think it's a good way to encourage people to use our package for implementing new methods. And it's kind of what I want to have it, like having it as a playground for people to try out new models and new methods. You can, after fitting, if you fit your model with different methods, you can compare them. You can compare the fits. Here we see for all the methods we've implemented, beside the pooled ones, the fit for the warfarin data just for 2 individuals. And they kind of agree, right? MCMC is a bit different here, but in general, they're all very similar. After then having agreed, okay, my fits, they look quite well, you might want to do uncertainty quantification. And what we provide for you is just one function that takes the fitted object, which is compute uncertainty quantification. For all non-MCMC methods, this is just by default the Walden approximation. You can also have the sandwich estimator, so Walden sandwich for asymptotics. We interface to likelihood profiler, which is feasible if your model doesn't take too long to calculate. Right? If it's too calculations are too long, then kind of profiling takes very long. But you can also use the chain object or the chain argument, which is the default for MCMC, and then it basically does Bayesian uncertainty quantification via MCMC sampling, and then you get credible intervals instead of confidence intervals. You can then summarize your UQ results. It gives you kind of this table with your estimates, standard errors, confidence intervals, or credible intervals if you're in the Bayesian realm. We also have plotting functions for this. You can also plot the posterior. You can plot the distribution of the estimator if you're in a frequentist setting. That's all implemented out of the box. Then a huge thing why we did this was because we wanted to have like a proper neural network integration, and Julia is particularly nice for this because it kind of just the neural network libraries like LUX or simple chains, they really interact quite well with all the other code. So when we extend the model, the PK model we've just seen with a neural network component that takes as input the concentration and some parameters, we kind of just rewrite the exact same model. We just define here with simple chains. You could also use lux.gl, a neural network chain. We define in the fixed effects just a neural network parameters with the chain. So everything is like the parameters are basically extracted then out of the chain automatically. We give it a function name, in this case, neural network clearance. And then we can just use this neural network with the name we have given it, right? So we gave it NNCL just in the code as of like a proper function. You give it the inputs, center and v. This is just a vector, and you give it the parameters. The parameters are just a flat array. So what we here basically create is just a flat array. And because, for example, in the pre-differentials block, you can transform these parameters as well. You could also use these parameters as means of a multivariate normal distribution, random effects distribution. And then what you get out of this distribution is just a vector of random effects that has the same length, which is just an array as well. And you can then put this in here as parameters as well, right? So this just as well. And then every weight and bias in the neural network would be a random effect. This has been done in some papers and is, I think, particularly easy to implement here in no limits because of this. It's just parameters are just an array structure, and all transformations are done for you in the back. We also have soft trees implemented. That's so popular compared to neural networks, but do similar things. Interface is very much the same. Just specifying them is a bit easier because they're not so complex compared to neural networks. When we fit them, it's exactly the same. So we just fit our data model with a fitting method. And here we see the comparison to the known dynamics in orange and the neural network in blue. Because this is in sample, it's not surprising that the blue one might fit the data points a bit better, and the Laplace marginal objective is better. It's just we basically give the model more freedom to fit these points, right? So this is more like a proof of concept that this works. Then after fitting your network, you might be interested in how your network actually looks like. So we can extract the neural network function quite easily with the get model funds here from the model. You can get the parameters from the model, and then you can just basically evaluate it because it's just, again, just a plain Julia function. We do not only have neural networks like via simple chains, but we also have normalizing flows. So they're directly basically invertible mappings or invertible layers that transform a base distribution, and then they're able to learn, in theory, more complex distributions from data. So we're not restricted to our prior assumption we make at the beginning. And takeaway here is this is just also just an ordinary random effects distribution, and you can use it like every other distribution in no limits as well. Here's just an example where we had like a really true mixture distribution for random effects here in black. We fitted the flow here in blue, so it got the bimodality, whereas the Gaussian prior here couldn't catch up the bimodality by construction. Hidden Markov models are very similar. So we just have, it's just an outcome distribution, discrete or continuous time hidden Markov models. They just basically one structure as an outcome distribution where you define your transition matrices here with beta random effects because they're between 0 and 1 and want to define probabilities. And then you define it as an outcome struct and everything no limits does for you under the hood. This was a bit more tricky because for the next data point, you always need information about the previous data point. So this is the only estimation limits where it kind of has this dependent structure. So this under the hood does a bit more than just the evaluations we have seen before. Yeah, how to contribute. So we might skip this due to time reasons. How to contribute. So we need your contributions. Definitely there's much room for tutorials, documentation, real world use cases, identifying a needed feature. We don't have covariate selection, for example, at the moment. We want you to implement your new estimation algorithms, find algorithmic improvements. We need more benchmarks. We mainly benchmarked it against NLMixR2 and SAMix. And yes, thanks a lot. Thanks to my supervisor. Thanks for you for listening. And thanks a lot for the Julia community and for all the packages we could build on. Yes, thank you for your attention.
Thank you very much. Are we having questions from the audience? We meet halfway.
Thanks a lot. It was very interesting, and I didn't know about the package. Do you consider, maybe you have already implemented some integration with some data formats, or are you considering integrating with, for example, PE-tab format? I know there are certain discussions, but I'm not aware whether those discussions have driven somewhere.
Yeah, that's a really good question. So PTAB was actually developed in our group. So this was a very lively discussion. There's currently the development of PTAB extension for nonlinear mixed effect modeling going on by another member of our group who's currently testing it for the Python version. And I know that he's in contact with Sebastian Pearson, who then wants to implement this in Julia. And then I'm in contact with Sebastian to implement this then with no limits. So this is very much planned, but I can't really give a time frame for this.
So you actually built your own Julia network.
Yeah, kind of.
Any more questions? Yes.
Have you had any or faced any challenges with excessive compile times for some of the larger models? And how do you handle that?
Yeah, that's a really good point. Especially initially, we opted for using Modeling Toolkit. Maybe we did something wrong because we had super huge compile times for Modeling Toolkit. When we use Laplace and we have the triple nested automatic differentiation, it's also for medium kind of models. The compile time is quite large. Yeah, that's something definitely that is the case. For Foki, it is okay-ish. For SIME and MCEM, it's definitely okay, I'd say. But yeah, for large models, the compile time gets very, very large. I experimented with then replacing one layer of automatic differentiation with finite differences, but that's actually nothing you want. I also tried kind of forward over reverse mode, but that wasn't really working for me. But there's there was a lot of painful moments. I was also thinking whether, because kind of what you showed, that when you create the code beforehand, so this is what Amici does, which was developed in C++ in our group, they kind of compile it beforehand, but yeah, in Julia, this wasn't really the way to go, I feel like.
Okay, more questions? Okay, then we can thank the speaker again.
Thank you.
And our next speaker is already preparing. It's Felix Jost von Sanofi, and he's going to talk about compartmental modeling and preclinical models.
So welcome from my end. Thanks a lot for the opportunity to present here and also your interest in our work. Um, I would like to talk about the challenge or how we tackle the challenge that we use or develop prediction methods to predict the concentration time curve purely based on the chemical structure or the amino acid sequence for large molecules and the chemical structure for small molecules. Where does this problem or challenge fit into our daily work? So I'm part of the pharmacometrics research group at Sanofi, and here we are supporting research projects until the project and the new molecules are then handed over into the clinics where they are tested. So we are in the research stage where over the research chain, more and more complex and sophisticated experiments are performed to study the compounds. We start with in vitro experiments, and as soon as the new compounds fit in our criteria, we then move from in vitro to in vivo experiments and test the new compounds then in preclinical species. And here we make use of the development of prediction methods, where on the one hand, we want to support the chemists during the compound synthesis to make predictions for new compounds and support them before already these new compounds are synthesized, so really de novo predictions. And on the other hand, when we then have a bunch of compounds where we need to decide which of them should be tested in vivo, we have then prediction methods for the prediction of concentration time profiles. And the main goal is here to reduce the number of animal studies and instead using those AI ML methods. Before we come to the three different projects I brought with you, you already saw how we can describe the concentration time profiles. One possibility is use compartmental PK models. These are empirical models, so to say, and depending on the profile, often those concentration time profiles have mono, bi, or triphasic curves, and those they can be described by these empirical ordinary differential equations. Another technique which is then important and we will make use of is allometric scaling. After we studied the compound in our preclinical species, the ultimate goal is then to predict the human pharmacokinetics and the human dose. Here again, an empirical approach which is purely based on the body weight. You can scale then, for example, the clearance, but also the volume of distribution using this simple formula. Either when you have one species, you have certain exponent like 0.75 for the clearance, you can translate it then to human, or when you have at least 3 animals, then you can perform a regression and estimate the exponent and make use of this exponent then for the prediction in human. This is highly empirical, but publications show that this works, and we will make use of this approach later on. But then it has a lot of disadvantages that when the compounds have species-specific metabolism, for example, then these approaches cannot be applied. Then another alternative would be physiologically based pharmacokinetics modeling. We also have it as a comparison in our approach, but I will not go into detail. When we think of AI ML solutions, then we split it into these different boxes where, depending on what kind of study we want to perform, let's assume a proof of concept study, we just pick from each of those boxes one methodology, or when we want to perform, for example, a comparison of different methodologies, then we make use of different algorithms or approaches from one of those boxes. And I have three different examples where we show these different selections. So we start with small molecules where we start with the challenge to predict the pharmacokinetics for one species, especially red. Then we move on to cross-species predictions, where we make use of all available preclinical data from the different animals, use this allometric scaling approach, and then predict human pharmacokinetics, and then we switch to biologics. The first example is predicting the pharmacokinetics for small molecules for rats. And when you look into literature, then in the last years, you see that different pharma companies also worked on this project, on this challenge, and we can then also see what kind of methodology they have used. When I came up and worked on this project, I first had the idea to combine also compartmental modeling with machine learning, but in a sequence approach. Then 2 years ago, Boehringer Ingelheim published and compared it with three other methodologies. So then I thought of using physics-informed neural networks, where we directly integrate the neural networks into our compartmental modeling and predicting directly the parameters of these small ordinary differential equations. But there was a PhD student from Novartis who worked on this and published his work. But he hasn't compared the different approaches with each other. So we then, we first had a publication where we also used three different methods from our colleagues from the US, and then we extended it where we now compared 5 different approaches and checked which of this approach best predicts the pharmacokinetics in red. And we used here, first of all, the chemical structure. This is then the numerical representation is more or less a 2000 long vector with 0 and 1s describing the structure. And this is our input of the neural network. And the neural network is then combined with a 3-compartment model where the neural network is predicting the 6 parameters of the 3-compartment model. And we are training the neural network on the concentration time profiles directly, which is a bit different than first performing parameter estimation on all the different profiles and then developing a neural network which predicts the PK parameters. So this is our physics-informed approach, and this we compared with 4 other approaches, looked at different evaluation matrices, and finally we came to the conclusion that this hybrid approach, where we also use the information how the concentration behaves in the body, this information together with the prediction method results then in 84% of predictions with fall within a 3-fold error. And this method we are now evaluating then also internally to see how we can reduce the animal studies with our prediction methods. But I also have to mention that the pure machine learning approach, which is actually a XGBoost approach, also achieved good results with nearly 78–80% predictions within 3-fold. So one can also discuss if an ensemble method combining both would make sense. Then we now extend this project that we not only want to predict the pharmacokinetics of one animal, but of all different preclinical species for which we are gathering data. First of all, in a research project, we start studying the compound in the mouse and the rat, and then at a later time point, when the project evolves, we also test the compound in non-rodent species like dog, mini pig, and cyno. But then you can also imagine that for these higher species, we have much less data compared to mouse and rat, such that combining now the data with an allometric scaling approach, we can make use of of the agglomeration of all data and develop a machine learning model, which then, based on the chemical structure and remember the body weight, can then predict these compounds, these parameters, and not only for the preclinical species, but then also for human, as we only have to change the body weight. I'm talking shortly about the data set, and you see here the different combinations for which we have for one compound. You see for mouse and rat, we have data of 500 compounds and 300 compounds. For the allometric scaling, we need combination of different animals. And this now then becomes even more challenging for the data splitting, because on the one hand, we want to make predictions purely on the chemical structure and learn a neural network which can predict based on the chemical structure. But then additionally, we want to have um, the information that for a certain compound, the allometric scaling behaves in this way, and therefore we have this exponent. For other compound, we have another exponent. So we are now need to learn these two different um, yeah, challenges. And there I then digged into data splitting. I used all available combinations in the training set that I have the possibility that I also can train this allometric scaling in addition to the chemical space, and then only used the combination of mouse, rat, and dog in the validation and test set. Our colleagues gathered a data set on human data with nearly 700 to 800 compounds, and they trained a XGBoost method on the human data set. So this is our reference. They achieved then values on area under the curve, Cmax, and the two different parameters, clearance and volume of distribution, of nearly 60% in the twofold area. When you look on the left-hand side, the method which is purely trained on the preclinical species and now predicting human PK profiles, we have a 20% point less at the moment. But together with an AI trainee, we are working to improve those predictions. But you also have to acknowledge the comparison that we have the one method which is purely based on preclinical species. The other one is really training a model on the human data. Now we switch from small molecules to large molecules. You can think of that we use the same method now for large molecules. We use pre-trained large language models to get numerical representation of the amino acid sequence. Here the data set is even more small. We only have 100 studies for this, but Sanofi already has a large data set, so 100 is large. And a proof of concept study showed that even this is working. With that, I come to the end of my presentation. I showed you 3 different projects, predicting rat PK, then we use cross-species allometric scaling, and prediction of antibodies. We haven't incorporated uncertainty, and also studying the chemical space. And with that, I thank you, and I want to acknowledge that this was work together with colleagues from Sanofi, working students who supported us, and thanks a lot for the group which are also working on these projects, actually our OS colleagues. Thank you.
Thank you for your exciting talk. I think we have time for questions.
Yes, thank you for the nice talk. You mentioned that basically you use the smiley representation to derive the parameters via neural network, right? So have you also plugged in more metadata? So for example, the species, the weight, or something like that, so that you basically incorporate that information also in the model?
For the allometric scaling approach, we also had then this additional information, the body weight. For the red predictions, we purely used the SMILE string, so the 2D structure of the small molecule. And we haven't used, for example, from packages, other descriptors. So it's just the 2D structure. Yeah.
Yeah, thanks for your talk. I have a very short question. So for the training or machine learning part, are you using the, for example, Flux.jl or to
Yeah,
do?
good point. Um, this machine learning concept was training on the job, so I had the chance to pick whatever language I wanted to use. From my PhD, I knew about Julia, so I decided I want to see how it's working on Julia. Here I used actually Flux correctly. Now the AI trainee, he is yeah, more trained on Python. He will continue the work on Python. But for me, I was excited to make use of Julia, so yeah, I implemented in Julia.
I have a follow-up. Because this training, procedure can be computationally demanding if you want to refine your model later and later. So, do you have any experience about, for example, the performance, computational performance, when comparing different, let's say, frameworks for machine learning and so on? And do you have any experience
Yeah, I
could
think
share with us?
for this is a very small machine learning problem with 800 studies. I think I had it then 10,000 data points. So one training just took me 15 minutes or so. So yeah, you, yeah, thanks.
Okay, thank you again for your talk. We will move on now with Ivan Borisov. He will talk about virtual population generation. Just a few more seconds. Everything is set up.
So, hello everyone. Thanks for the opportunity to be here. Thanks for coming to this talk. I'm going to speak about virtual populations in quantitative systems pharmacology, and in some sense, it will continue the presentation by Elizabeth. Those of you who attend systems pharmacology conferences have seen probably lots of posters and talks about virtual populations. It's a hot topic. There are certain reasons for that. But for general audience, I'll briefly introduce what virtual population is and why they matter. Then we'll discuss the problem of virtual population generation, the main challenges involved, some of the existing approaches, and the ways to address them. And finally, I will speak about the packages we develop and problems we encounter during virtual population generations. Just a few words about myself. I work at Bio, a company that develops models and tools for pharmaceutical companies. So as a result, my perspective on this subject is somewhat shaped by the questions we receive from our clients. So to talk about virtual populations, we need some basic ingredients. The first is a mechanistic model, in our case, usually a system of differential equations which describe the action of a drug in the body and the underlying biological processes. The model has a number of unknown parameters, and by changing these parameters, we represent biological variability between different patients. We simulate the model with those parameter sets and obtain a range of model outputs. And then we have clinical data observations from clinical trials that describe how real patients respond to treatment, and our goal is to make the model outputs consistent with these clinical observations. So in principle, this is a model calibration problem, nothing surprising so far. But in case of clinical trials, we are usually interested not in finding the best parameter values which describe the average patient. What we are interested is in to capture the variability of patient response to different treatments. And this means that instead of a single parameter vector, we are interested in a collection of parameter vectors or distribution of model parameters. So here comes the idea of virtual population. So virtual population is a set of different parameterizations of a model reflecting individual and population level characteristics of a real clinical cohort, and the member of such population is often referred to as a virtual patient. The terminology may vary a bit from paper to paper. So far, this looks like a fairly standard population modeling problem, and in some sense similar to what mixed integer, what mixed effects modeling field does. But in real QSP projects, at least in projects that we have, we constantly encounter certain challenges that make this problem much more complicated. First of all, because of different restrictions, for many therapies, we don't have access to individual patients' data. What we usually have are summary statistics describing patients' response to therapies, which means percentage of responders, quantiles of time to response, and other statistical summaries. The second challenge is that these clinical efficacy endpoints are usually not direct outputs of the mechanistic model. For example, the model may predict the change in tumor size over time, while clinical data report the percentage of patients who respond to treatment, and we can calculate those statistics only once we have the entire candidate population. So this problem becomes multidimensional because usually we need to consider several therapies, dosing regimens, clinical endpoints simultaneously. Often there are some additional restrictions. So ultimately, what pharmaceutical companies would like us to have is a virtual population that can consistently describe the observed responses across different drug treatments, regimens, and account for different constraints, and then be used to make reliable predictions for new doses or drug combinations. A number of approaches have been proposed to generate virtual populations, but the mentioned challenges, at least to our experience, limit the applicability of those approaches. So what we propose and what we use often is based on the so-called selection approach. The general outline of this method was presented in a series of publications by Richard Allen and colleagues from Pfizer. It consists of three main steps. First, we generate the so-called plausible population. So we sample parameter values from predefined distribution, simulate the model, and apply accept-reject criterion to retain only those parameter sets that produce biological plausible outcomes. As a result, we obtain a set of physiologically plausible patients, as they are called, and this is a already challenging step because we want the plausible population to be both large, diverse, and in practice, we often reject more than half of the simulated candidates. And there are some ideas how to make the generation of those plausible populations more efficient, for example, using machine learning surrogates. Once we have this plausible population, it does not necessarily reproduce the clinical data. So in the second step, we need to select a subset to subsample from this plausible population to select the subset which reflects the clinical data, and this subset becomes our virtual population. Finally, we perform validation by testing the selected virtual population against the data which was not used in the selection process. So the concept works quite well. However, in the projects where we have multiple therapies, multiple endpoints simultaneously, we found that the original approach was not much efficient. So we developed an optimization-based selection procedure. S- The idea of this procedure is very simple. Each candidate in this pre-generated uh, plausible population is associated with a binary decision variable indicating whether this patient is included in the final virtual population or not. For each therapy and each clinical endpoint, we define the component of the objective function that measures the discrepancy between the prediction of the selected population and the corresponding clinical data. And the objective components are combined across endpoints and therapies into the objective function, which is minimized with respect of the binary decision variables. So as a result, we obtain the optimal subset of patients, namely our virtual population. We used mixed integer optimization. Here, I'm not an expert in this field, and in general, those problems are considered hard. So one of the key ideas is to formulate this endpoint specific objective functions using linear or quadratic functions for the of the binary decision variables. So we've implemented this approach in the VPOP-ME package together with some other supporting Julia packages. This is a still work in progress, so many things can change, including the name. So it's not yet registered in Julia general repository, but the package is available and there is documentation and tutorials. One of the main things we tried to do was to provide objective function components for different types of clinical data we commonly see in practice for quantiles, response rates, survival curves, and so on. And the overall workflow is quite straightforward. You load the data, load pre-generated plausible population, specify which endpoints should be matched, and the package construct the optimization problem, performs the subset selection, and outputs the virtual population. The mathematics and some implementation details can be found in the docs. So we have a number of tutorials in the package. I just quickly say about a few words about this tutorial. Here we examine a non-small cell lung cancer model, and as in the original study, we start with plausible population of 1,000 candidates and select 112 patients from it as a virtual population corresponding to the number of patients in clinical study. We fitted the population to 2 treatment regimens, and there are 3 endpoints considered. The left column shows the original plausible population here and compares the statistics of this plausible population to the clinical statistics. As expected, the plausible population is biologically reasonable, but it doesn't reproduce the clinical data. The right column shows the virtual population obtained after the selection procedure, and we see that it fits the data quite well. You can see this tutorial in the docs. I wouldn't speak much about strengths and limitations, just one phrase for the end of the presentation. I think there are that QSP field needs a lot here. We need tools to solve virtual population problems. We need data formats to define those problems. We need benchmark models. So hopefully there are many people who are also interested in this, and all contributions are very welcome. Thank you for your attention. I'd be happy to answer questions if they appear.
Thank you for your question, for your talk. Sorry. Do we have questions? Maybe one quick question. Oh, sorry. Where was Manuel?
Yeah, thank you. Why was Julia so well suited for implementing this compared to other languages?
Well, okay, it's good question. The question which has maybe answered differently, but the reason is that we use Julia a lot for simulations. So it is nice for us not to go into other language. I'm not sure about the strength of Julia in mixed integer programming. We didn't explore that field that much, but it has nice optimization packages which have interfaces to common tools used for the mixed integer optimization. So probably that's the reason. And further, we would like to use this package to interface it to some data formats like PETAB maybe. That's yet another reason.
Okay, thank our speaker again. And for the last part of our mini session, we are going to switch a little bit the topic. We are going to scientific computing and how it can be applied to drug discovery. The first on the stage is Diego Zaire. Thank you for being here today. And everything works soon. Yes, thank you. So we will have lessons about alpha conformers. Thank you.
So, hi everyone, thank you for the introduction. So this is reproducible bioinformatic pipelines in Julia. So the lessons I learned by implementing it in alpha conformers. I will first start with the biological problem, and then I will present the pipeline itself. And finally, I will show why Julia is useful for this, it's helpful. What are the tools Julia gives us for reproducible pipelines in bioinformatics? So first, the biological problem. The biological problem is the one of predicting alternative conformation of proteins. So proteins are machines. Our machines need to move in order to perform their functions. So proteins move, but it's very difficult to get a movie of how the protein is moving when performing its function. And instead, what we have is like a small frames of the movements that we can get by experimentally resolve some protein structures in different conditions. So for example, we can have some small molecules, so the ligand of the protein, and we can resolve the structure in presence of the ligand. That will give us the ligand bound conformation that we are going to call here the hollow conformation of the protein. And also we can resolve the same protein structure without the ligand, and that will give us the apo conformation, the unbound conformation. And we can hope that this gives us some hint on the mechanisms of the function of the protein. There is a tool that I guess you already know, that is AlphaFold2. So AlphaFold2 is basically a Nobel Prize winning method, if you think, for predicting model structures based on protein sequence, but it has a flaw that is only able to predict one single conformation, or if you run multiple times AlphaFold2 with the same inputs, you are always going to get the same conformation. And in general, in 67% of the cases, is the hollow conformation of the protein, so the one is bound to the ligand, even if the ligand is not included in the modeling process. So we want to solve that. We want to use AlphaFold2 because it's very accurate, but we want AlphaFold2 to give us the different conformation of the protein. And we think that by giving particular inputs, so the right inputs to AlphaFold2, we can steer the predictions. So which are the inputs to AlphaFold2? In general, we start with a sequence, but in fact, the pipeline is going to create a multiple sequence alignment of homologous proteins. That is the main input, in fact, to the neural network of AlphaFold2, and also a set of structural templates that is going to look in structural databases as the PTB. And basically what we propose is to give particular and custom multiple sequence alignments and custom templates. The idea is that if we have similar, structurally similar proteins, so homologous proteins with similar structures, we can see that these proteins can also share other conformations. So let's imagine we start with some carry structure. For example, you have run AlphaFold 2 and you get a model for the holo conformation. And you can use this as the carry structure. And you're going to look in the databases for structures that are similar to this. And for example, you find this dark green dot that represents a similar structure. And your objective is to model the APA conformation, so the other conformation of the same protein. And hopefully, if we know another conformation for the dark green protein, maybe it's also similar to the target conformation we want to model, and we can use it as a template in AlphaFold 2 to guide and steer the prediction. So that is the general idea, and we have implemented that as a Julia package. So all the pipeline is implemented in Julia. All the orchestration is done only in Julia without needing bash scripting or Python glue code. Also, all the data processing is done in Julia, so many of the steps are Julia code. And this is thanks to the Julia package ecosystem that has grown a lot in the last years. And in particular, there is a lot of tools for bioinformatics. One of the package I use in Alpha Conformers is Mitos. That is my package for dealing with multiple sequence alignment and protein structures. I'm going to present the new stuff in Mitos in a poster tomorrow. So if you want to check. I also use BioJulia. In particular, BioAlignments is super nice for aligning protein sequences. And I also use BioStructure for some utilities that is not included in Mitos, but you can use both packages together. They interact very well. I also use data frames, clustering, and so on. So many packages of the Julia ecosystem. So coming back to the pipeline itself, so the first step is to look for structurally similar proteins. And there is already an external tool that solves that is called FoldSeek. So FoldSeek takes a structure as input and is going to look in databases of protein structures for similar hits. In particular, we take our carrier structure and we look in the protein data bank that has experimentally resolved structure, but also into the models from the AlphaFold DB. That is going to give us a set of possible templates, a set of structure, and FoldSeek can also be used for creating a structure-based multiple sequence alignment that we are going to use. Then the FoldSeek hopefully will give us all the structure for a single protein, but it's not working like that always. So sometimes it misses some conformation. And to solve that and hopefully get the correct templates, we use the CIF module of Mitos. So CIF is a database that links PDB to other databases. In particular, it links to the UniProt database. So we use the UniProt identifier as the identifier for the protein to look for other structures of the same protein. That will give us the extended template set that is more complete. And that is a lot of structures. So we are going to clusterize because the expensive step here is to run AlphaFold 2, and we cannot give all the structures we found as templates because that will be very costly. So we are going to reduce redundancy by clustering the structure by structural similarity. That also have a benefit that we can create a multiple sequence alignment that is not too large and that represent exactly the structural information we need by only including the sequences that belongs to the proteins in the cluster. For doing the cluster, we also use MITOS. In particular, from the MSI module, there is a Hubble one clustering algorithm implementation that is parallel. That is very nice because we have many structures, so we need it to be fast. And to calculate the distance between the structure, we use an external program that is USAlign. USAlign will take two protein structure and is going to return the RMSD, so the root mean square deviation. That is the metric we use to say whether two structures are similar or not. So we implement that, we pass each cluster MSA and set of structures to AlphaFold 2 to predict a possible conformation. And if we do that, for example, here we have one case example, an uncharacterized protein from a bacteria. So we have the apo conformation of the carry conformation, and we want to predict the target conformation that is the hollow conformation. And each blue dot here is a prediction from alpha conformer. We can find this that is the closest to the target at 1.7 angstroms, which has a very good model, in fact, of the conformation. So we can see that it works in this case to steer toward the correct conformation. And we have also tested this with many other proteins and against other tools for solving the same problem. So in our case, we have found that alpha conformers, that is here the last bar, has the higher number of good solution, in particular for conformational changes that are lower than 2 angstroms RMSD. So it's very good at capturing these subtle conformational changes in comparison to other tools. So it's very nice that we can implement all this in Julia, that it works and everything. So I want to talk a little about the Julia tools that allows these reproducible pipelines. In particular, the package manager and the JLL packages. So bioinformatic pipelines, as alpha conformers are used as an example, will use many external tools to do one task. In general, these external tools has been developed during years in different labs. So we are not going to re-implement everything in Julia or something like that. We are going to use these external tools, and we need to make this use easy. So for example, here in the pipeline, we have three main tools. We have FoldSeek for searching similar proteins at the first step, USAlign for the clustering of the structures, and CollabFold, that is the AlphaFold 2 implementation we are going to use. We use CollabFold because it makes easy to give custom multiple sequence alignment and custom templates. Julia makes really easy to run external tools because you have commands that are the ones you write with the backsticks. So basically, here you have two commands. The first is cosay to say hello, JuliaCon. And then, for example, you can use the pipeline function to concatenate commands. So, for example, the output of the first command is going to be passed as an input to the second command. That is simply a seed instruction to change hello for hello. And you can run pipelines and commands using the run function, like in this example. And we can use the same with JLL packages. So JLL packages are normal Julia packages that distribute binaries. They are versioned and they can be managed by the Julia package manager, yeah? So basically the name of the package is the same as the name of the tool, and every has the suffix of underscore JLL. You can add it as any other package, and the PKG will take care of install the package and all its dependencies that are also JLL packages. So for example, here, FoldSeek depends on bzip2, We don't need to ask the user to install bzip2 and then folseek. Everything will be done automatically. So you can simply import the JLL package, and every JLL package defines a function that has the same name as the executable of the software. For example, here is folseek. And if we execute this function, we'll give all that the command needs to run this particular tool. So here we are going to create a command in which we interpolate the result of the folseek function. That basically is running folseek. And we are going to give after that the arguments. For example, here simply version to ask for the version we have installed, and it's going to respond with the version of folseek we have used. So Alpha Conformer uses JLL packages for folseek and US-align. We don't use it for collab-fold because collab-fold is in fact is a Python package that is a neural network, so it's very huge, and we use a singularity image for that. So we use a container for that, but still we call it using the round function. Thankfully, there is already a lot of JLL packages for bioinformatics. So, for example, these are some tools I have used, as MAFT for multiple sequence alignment, MN62 for looking for homologous proteins, and then also PhyML for phylogenetic inference, but there are more than 50 packages related to bioinformatics that contains binary as JLLs. And if you go to this repo, you will find the complete list of all those. And if you have developed a bioinformatic tool that can be distributed as a binary, you can also distribute it for the Julia community as a JLL package. The process is quite simple. So basically you need to create a recipe that is a Julia file that is going to give all the instructions needed to compile the software in different architectures. You can find a lot of recipes in the Yggdrasil repository, yeah. And you can look there for a similar one and adapt it to your software. Or my preferred way is to use the binary builder wizard, because it's going to guide you with options and questions in the creation of the recipe. Also, if you use the wizard, it's going to test that the recipe is properly working. But if you have modified an existing recipe, you can test it locally by running the recipe. And once you are happy with the recipe, you can create a pull request to Yggdrasil to publish the recipe. When it's merged, it's going to automatically create the JLL package and making it available for the Julia community. And basically, you need to iterate in continuous integration failures that is going to appear, and also answer to the review feedback. The people working there and doing the review feedback, they are very nice and helpful. They always help me to get it right. So it's not very compiling something is tough, but it's not so complicated. So alpha conformers has been the example, and it doesn't depend in any Python dependency. But in case your pipeline depends on some Python tools, you can still be reproducible by using Conda Pkashi. So for example, here I'm using Thorax. That is a tool I developed during 2.5 years in Python. So I don't want to re-implement the tool entirely in Julia. So what I did is to create a Julia wrapper, and to ensure that every people using this Julia wrapper has the proper Julia environment, I created a Conda PKG toml file that is going to describe the exact version of Python you need to use, the exact version of the package you need to use, and so on. So you can have a reproducible Python environment also include in your Julia workflow. So to recap, I have shown how we can create a pipeline as alpha conformers that solve a biological problem. And you can use Julia to do all the orchestration. You don't need any other external language, and you can use that to bring together so the Julia code with any external tool in a single workflow. So I want to thank Julie Daniel that has performed most of the code of the alpha conformers. She has also tested the pipeline, tested against the other methods and so on. Also Lucas that has participated in the development of the pipeline. And I want to thank you, all of you, for your attention.
Thank you for your talk.
So,
I found it incredibly helpful to have it all put together for some point, because we're still missing in bioinformatics some of these tools, right? We know from other languages. Are there any questions? Okay, I have to run.
yes.
Um, so using JLL packages implies that you'll have to interface with it as if it was, I don't know, like a command line interface program. Am I right?
Yeah.
Um, is there a possibility of like using those JLL packages as a dependency to expose the API for, I don't know, for example, in full seek, it would be much easier to have like functions in Julia flavor to make code much more idiomatic and be able to read it and I don't know provide multiple dispatch and stuff like that, and use the as a backend, let's call it the full seek binary, for example.
Okay, so in fact, inside the pipeline, each of the steps that call an external tool is inside actually a function that takes all the parameters. So all the API inside the pipeline is very Julian, let's say. So you don't do run, but you call run full seek function that will take the arguments and pass it to the full seek binary. So yeah, in general it is like that. Then also I mentioned only the ones I have used in this pipeline that is basically binary products executables, but you can also have libraries and then you can use CCall, for example, to interface those. I didn't use any of those in this pipeline, but yeah, it's also possible.
Over here. Just to answer that question, if you want to look at ncbi blast.jl, it's just a thin wrapper around the blast JLL. So it does exactly what you're talking about if you want to see that. For you, I was just curious, you mentioned that one of the pieces of software you don't have a JLL and you're using a singularity container instead. Is there a reason that you don't use conda package for that so that you can bundle everything together? Is it just because it's simpler on your end, or is there some other technical reason to use the container?
Yes, yes, if it's not really like a Python package that you can install easily because it's since it's a neural network stuff, it also depends on some CUDA libraries and so on. So it's more easy to have everything back as a container. And in fact, Collab Fall has the official Docker image that we use to create the singularity image. So it's the same as the official.
Do we have more questions? No? Okay. We are still having time for questions or for discussions, comments, ideas. Okay, then like, yes, yes, do more.
sort of along the same lines. I've for a number of things, I sort of run into this problem. Like, do I do conda package? Do I do my own sort of wrapper? Do I use a container? Is there any Julia functionality, or should there be Julia functionality for building and downloading and using Docker containers, kind of the way that we have JLL packages? I think it'd be nice to have sort of a more contained way to use containers in an easy way.
Yes, that will be awesome to have. We don't have, or I haven't found any way to do that. But yes, it will be super awesome because right now I need to ask the users to download the image and they need to install Singularity themselves. So having something more automatic will be nice.
You may like to talk to Jakob Quinn about that, who had a presentation on from based on Julia services. He was quite a big fan of Harbor.jl that could apparently do something with Docker. So
I saw that on the schedule. I didn't make the topic.
well, he's probably around here somewhere. If nothing else, you can find him on GitHub.
And by the way, this might also be a good point to announce the Birds of a Feather session. I will come to you. The Birds of a Feather session on Friday. It's organized by the BioJulia community and the BioHealth community. And we will also be there to talk about the needs of these fields as well. Yeah. Can you tell me again what's the time? 3:45 or something, right? 3:40. Yes.
Yeah.
3:45. Yeah, great. So please join us there so we can discuss this further, what we can do.
Team effort. Thanks, Jennifer. So just along the same lines, I guess it would be awesome to gather your work on collecting all the information of these JLLs into, if you want, into the BioJulia, like to have it more discoverable, to put it on the BioJulia website and make it easier for others to contribute to, I think, to offload you and to maybe make it more visible and easier for everyone, if you feel like that's a good idea. So just a small comment.
Yeah, sure. We can move the file to the BioJulia. Yeah.
Great, thank you. So I think there's definitely something we can also discuss during the poster session. Our next speaker.
Thank you very much.
Yeah. Thanks again to the. Sorry. We will move on to the next speaker, and then I will change quickly to the chair. This is Professor Hilbrand, and he is going to chair the last part. But first of all, we have JuliaCon today here, and she already told me that she's actually doing both, standing in the wet lab and coding in her free time kind of thing. So everyone, welcome Julia. If you try to turn it on and off again.
Oh, okay. No. Yeah, it's not moving. Good afternoon, everyone. I'm Surya Sekran, a PhD scholar in the Department of Biotechnology at Sri Ramachandra Institute of Higher Education and Research, Chennai, India. So, thank you for being here today. I'm excited to present JuDoc, an open source machine learning driven platform for virtual screening of phytocompounds. So, it's a target agnostic framework built entirely in Julia for high fidelity computational drug discovery. We have also filed an Indian patent for this novel method. So this work is done in collaboration with my research advisor, Dr. Paul, who's an assistant professor in the Department of Biotechnology at Srihar. So high throughput virtual screening is the initial phase of any modern drug discovery pipeline. So the primary goal is to systematically identify the potential compounds that can bind to a specific protein target. So physics-based molecular docking is the gold standard technique which accurately simulates how a molecule physically fits into a protein pocket. Phytocompounds are also heavily screened in this HTVS for novel therapeutics. So there are many challenges in traditional HTVS. So among which the key challenges include physics-based docking, which is it requires extensive computational resources, and also it is expensive. It requires a vast amount of memory to process libraries at scale, and it is also time intensive, often taking days or weeks to return actionable hits. So we also need a significant domain expertise in computational chemistry and structural biology to set up and interpret these complex docking simulations. These pipelines rely on multiple disparate tools and brittle shell scripts, such as crossing between RDKit, OpenBabel, and C++ engines like Autodoc Vina. So to overcome these challenges, we introduced JuDoc. It is a complete end-to-end Julia application that replaces slow physics simulation with a fast machine learning model. So our core regressor is built using a multi-output random forest regressor that simultaneously predicts binding affinity and the interaction profiles. So the application runs on a local host through the genie.jl, providing a modern browser interface. So a user need to drop their SDF files to orchestrate the prediction automatically. JuDoc drastically reduces screening time from minutes per compound to milliseconds by utilizing the pre-trained machine learning model. Uh, the predictions are displayed in a rank table within the GUI and are saved as a clean CSV reports for documentation and analysis. Our core engine is powered by Python call.jl, which can call RDKit and scikit-learn directly in a unified framework. We have implemented JuDoc as a Dockerized Linux application for 100% cross-platform reproducibility and simplified setup. So our rapid prediction workflow replaces slow physical simulation with a high fidelity machine learning model where the user has to input their compounds as the SDF files. And once the application fetches these compounds, it instantly calculates a vector of 30 physicochemical descriptors and using the RDKit feature. And the binding affinity and the interaction counts are predicted using the pre-trained machine learning model, which acts as a surrogate for the traditional physics-based molecular docking. And based on the predicted binding affinity and the biophysical interactions, JuDoc calculates a custom score, which we call the doc score, and it classifies the compounds as potential, putative, or not active based on this doc score. So as I have mentioned earlier, JuDoc can predict a compound to be potential, putative, or not active based on a custom doc score. So the intention of the formula is the compounds should be classified not only based on the binding affinity, but also based on the number of hydrogen bonds, number of hydrophobic contacts. So we have given a distributed weightage in the formula. So JuDoc is a biologically nuanced predictive engine. We've implemented a multi-output random forest regressor, which is an ensemble training method that constructs hundreds of decision trees to make a final average prediction. So each tree trains on a random subset. An input vector passes through all these trees and outputting the binding affinity, hydrogen bond counts, and hydrophobic compounds. So the final average reduces variance and noise. So this captures the physical correlations between a ligand structure and its complete biophysical profile, like how binding affinity scales with the number of hydrogen bond counts. Unlike standard QSAR models, this allows learning complex nonlinear rules. So our validation used a rigorous scaffold-based data split to ensure generalization against unseen chemical structures. So we have validated a multi-output random forest regressor model on 17-beta HSD1, which is a critical target in breast cancer. So 17-beta hydroxysteroid dehydrogenases, hydrogenase type 1, drives estrogen production. So it converts estrone to estradiol, which is the most potent form of estrogen. About 60% premenopausal and 75% postmenopausal breast cancers are hormone dependent. So our goal is to find isoform specific inhibitors for this critical target, as currently there are clinical zero drugs that are clinically approved. So before training our machine learning model, we benchmarked our pipeline against the enzyme's natural substrate estrone, establishing a strict baseline of minus 8.1 kcal per mole to ensure we only select through high affinity competitive inhibitors. So our validation results shows an RMSE of 0.58 kcal per mole for binding affinity, which shows that our model replicates the physics-based docking, while 79% of classification accuracy shows a strong classification, and 0.4 uh, F1 score shows a balanced precision recall. And also, 0.82 of AUC ROC shows a high discriminative power. So we seamlessly calculated these metrics entirely within our Julia pipeline by bridging the data frames.jl with scikit-learn through python call.jl. So here's a short demo of a JUDOC application in action. So as I had mentioned earlier, JUDOC is a Dockerized application, and it can be installed in any machine with 100% reproducibility. And application runs on a local server, so it can be used on any browser. It can be opened using any browser. And once the GUI loads, the user can select any protein target, which will then select the model, and we can start the analysis. We then initiate the process by clicking, the Start Analysis tab, and each compound is then screened in a sequential pipeline. So once the process is complete, we can view the results using this View Results tab. And the results are displayed on the right side in a rank table, where we can view the predicted binding affinity, predicted number of hydrogen bonds, a custom dot score, and the classification, whether the compound is potential, putative, or if it is not active. So this table is saved within our application for interpretation and analysis, and also it is also saved as a CSV file in the user's home directory. So JUDOC is designed from the ground up to be a completely target agnostic framework. So it features a modular model registry that currently holds the optimized models for both 17 beta HSD1 and aromatase. It is an open source framework where the scientific community can train and contribute models for any receptor of or protein of their interest. The complete step-by-step Julia pipeline used to train these models is fully documented and available in our GitHub page. So our future work will include parallelism. We will implement a RAM-aware multiprocessing job scheduler using the distributed.jl to safely saturate our multi-core hardware and reduce time. We will enhance the predictive power by integrating protein ligand interaction fingerprints and incorporating 3D descriptors to better capture the specific geometry of the binding event. We will be adding a module using open source models to predict the admit properties. So the results table will also include a drug likeness score to prioritize hits that are potent and viable drug candidates. So we'll also build a feature to perform automated structural modifications on high scoring hits and use the machine learning model to instantly rescore the new analogs guiding medicinal chemistry efforts. So in conclusion, we have successfully built a complete end-to-end Julia pipeline for high throughput virtual screening. So this work demonstrates Julia's unique capability to orchestrate complex multi-language scientific workflows while bypassing massive computational bottlenecks. Thank you.
So, thank you. Thank you very much. Are there any questions from the audience?
Thank you for the talk.
Yeah.
I have a question about the formula for the docking score,
Yeah.
which you showcased on slide 6, I believe.
Yeah, the doc score.
Yes, I was wondering how you determine the weights for the different contributions that make the dock score. For example, why the affinity is twice as important as hydrogen bonds.
Okay, so in medicinal chemistry, like the thermodynamic uh, binding affinity carries the, it's like more responsible for the binding event. So like we have given the maximum weight for the binding affinity, and hydrogen bonds, it shows the target specificity. So we have given a moderate weightage for hydrogen bonds, and for the hydrophobic contacts, it's responsible for the stability. So like we have given the least weightage for it.
Are there further questions? If not, I have one. What I actually didn't get is where you include the receptor in your model. So the protein, how is that handled? Do you need to pre-train it with known binders and non-binders, or?
Yeah, like you're asking about the training, the model.
Yes. So you build a model specific for a particular receptor, right? Or
Yeah.
okay. And for that, you use basically information about binders and non-binders.
Yeah, based on, I've taken compounds based on 3 categories.
Yeah.
And I've benchmarked the natural substrate estrone. So estrone is 17 beta HSD1's natural substrate. So it has a binding affinity of minus 8.1. So I use that as a cutoff.
Okay, and you trained it on a database of known binders and or
We do the traditional docking with Autodock Vina.
Okay.
Yeah.
That step I didn't get.
Yeah,
Yeah,
that's
thank
all.
you.
So we have trained this model with 261 compounds right now. We will be doing it in higher amounts.
Okay, thank you. Okay, thank you very much. That part I didn't get. So let's thank the speaker again. So the next speaker really doesn't need an introduction because she introduced herself earlier, but still, that's Jennifer Leclerc, who is doing her PhD in my group. Jennifer did a great job of chairing this session so far, but we thought it would be a bit weird if she would chair her own talk. So that's why I'm standing here now.
With a beamer.
Yes,
which we know that sometimes it just doesn't work here.
Okay, great.
But this time it works immediately.
And Jenny is going to talk about effects of stochasticity on molecular minimization.
Yeah, thank you for staying so long here. I know everyone is already thinking maybe about lunch and most important about coffee. I try to make it short. We are talking about molecular minimization. And if we are talking about minimization or optimization in general, I think it's always helpful to have this picture of a landscape in mind, where we are starting at some point and we want to go down to the deepest valley, or if we want to go up to the maximum peak. That should be better, right? I said it's always doing something strange, this beamer. But now it should work. No? No. Okay. Let me, maybe it, no, it doesn't do what it's supposed to do. Was too good. It does do what it's supposed to do. So coming back, so we are thinking about landscapes and we are thinking to go down to the valleys we are interested in stochastic in the minimization, and in molecular minimization this term is called potential energy surface. So we have a configuration, and if we change a little bit the atoms, then we're finding maybe better configurations. And you see one of these potential energy savers is here, and we have 2 minima. One is here and one is there. And typically these landscapes are high dimensionally and very complex to find. That's why we brought it down in this ways that we can actually picture that. And we have similar landscapes in machine learning context, which are the lost landscapes that you can see here. Maybe you go to this site because it's actually really fun to just look at these pictures of lost landscapes, and you can interactively just search them. But in principle, they share a lot of common features. And what they are doing in machine learning is to smooth this high complex landscape is to introduce stochastic gradient descent. And we hope that we can do the same thing with our landscape. To just let me quickly summarize what is molecular minimization for those that are maybe not too familiar with it anymore. Why do we have to do that at all? Because our structures normally coming from the PDB, they are not perfect, they do not resemble nature. That is really hard. And what we have to do is to prepare that, and then sometimes we still contain steric clashes, atoms are overlapping. To be honest, it's a mess sometimes. But we have to do that because if you have these steric clashes and you're running your molecular minimization, molecular dynamic simulation, then they can cause harsh gradients, and that means your energy is exploding. So we are actually in our group, we are developing biochemical algorithms, JL, and I don't want to go too much into details because I gave a talk 2 years ago in Eindhoven about that. It's a library for molecular analysis and simulation, and it's based on a C++ framework that was very popular in 1996 and also 2010. It has a really broad user community, and it has functionalities for reading, pre-processing, and analyzing molecular structures, mapping, and so on. But coming back to the minimization, the classic minimization that you can that is typically done in structure-based bioinformatics, that is with a LBFGS or other quasi-Newton approaches, and we can already do that in biochemical algorithms. You load your protein or alanine dipeptide in this case, you run your optimization, and you can see, okay, the energy is minimized, that's fine. So why are we actually looking in other things? First of all, the problem statement again, what we are giving is a starting configuration, and we are interested in finding another configuration where the energy is slower than the starting configuration, the gradient is equal to 0, and the Hessian has to be positive semi-definite. Yeah, so that's the proper mathematical formulation for our problem, what we have here. But what is actually our objective function? So which function are we trying to optimize? And this is the molecular mechanic force field energy function that is basically a sum of different turns modeling different effects of the force field, for example, stretches, bond angles, or also the non-bonded interactions like electrostatics and van der Waals terms. The big question is, how can we implement a mini-batching strategy on that function? So we basically came up with 2 approaches. The first one, I will just call now the fixed composition batching, where every batch consists of if we are having enough stretches, bends, and proper torsions, or we have the flexible composition where we said, I don't care, just randomly select the interactions you have. The only rule we had, of course, the batches have to be the same size. And due to implementation reasons, we just started with the flexible composition. And we tried it out with different learning rates with optimization JLL with an atom solver. And in principle, we can see that the energy is decreasing. So that was fine to see that it works. What not so nice is that, of course, it takes a lot of time sometimes until it converges. And what we can also already see is that the learning rates influences how fast we can reach our convergence. Then that is on a very easy protein, of course, tested. And we also test that. That's the good part about Julia. You can just use another solver for an optimization JL and try it also out. And we also see that different solvers perform, of course, differently. And sometimes it can really take a long time to actually see still the process. So what we did then, of course, learning rate, I showed here, I don't know what, with a different learning rate, if we increase the learning rate, then these rather smooth curves are going to fluctuate. And that is very interesting for us because we can actually see increases in the energy that are then going to slow down a little bit again. And this is where we assume that we can use that to jump over local minima so that we can actually reach a deeper minima. That is what we assume to be. We also take a look at the fixed composition strategy after we re-implemented our force field. And what you can then see is I tried it here with different proteins. So on the right side, obviously, the energy is increasing. On the left side, it doesn't. We know that. And we are still looking at why it's actually increasing again. And but what we can see it in both cases, we have these nice little curves of energies. And that can be explained because the atoms are, during one epoch, the atoms are actually maybe put together. And the other interactions make sure that if they are too close together, that they are pulled out again. So we can see this, that actually we have these little jumps over there. Just to let me summarize, because we also want to have some time, the batch size, the batch composition, and the learning rate are important hyperparameters. We are planning to carefully tune them. Then we want to escape local minima to facilitate the exploration of this surface. And we are in the future, we are definitely looking for a learning rate scheduling system. We want to try out multiple starts and perform this systematic hyperparameter tuning. But we are also looking for use cases where we can explore this energy landscape. With that, I would like to come to an end. Just as I already said, we are developing biochemical algorithms there. And even if these are just a few lines out code, you know how it is. It's long discussions, countless cups of coffee, and different approaches to get to the end. And therefore, I would like to thank my supervisor, Andreas, and Thomas Kemmer. We are basically jointly developing this software tool. And if you are interested in it, and then I would happy to see you at our poster session. And now just a small riddle. If you're already thinking about lunch, this will be active soon in your stomach, or at least similar to that. So with that, I would like to come to an end. Thank you for your attention.
Thank you very much, Jenny. So, are there any questions? Oh, there are already a lot.
Hi. Thank you for the talk. On slide number 9, you show some plots of the different optimizers and how they perform. So the y-axis is energy per kilojoule, which is kilojoule per mole. For different optimizers, I was expecting that they converge to a single value. Or
they do if you take more steps.
Oh, okay.
It just takes longer time to they converge. It goes on and on and on.
But for molecules, they often don't. In this case, they do, because it's a simple example. But for molecules, you have a very, very rough surface with a huge amount of minima, local minima, interspersed with everything else. And different minimization strategies typically end up in different minima. That's one of the reasons why we thought about stochasticity in order to find minima that generalize more, like in the sense of, you know.
You mentioned the great talk, first of all. Thank you. You mentioned the hyperparameter tuning and needing to sort of carefully tune these things. How generalizable are the hyperparameters? Is it like every single protein you have to do a separate, really intense tuning step, or do you think that some of these hyperparameters are going to generalize maybe across classes of proteins or something like that?
That's a great question, actually. So the thing is, it's actually much more complicated because when we are moving these atoms, then our force field, our objective function is changing, because it can happen that you have multiple that you are actually having new non-bonded interactions. So the hyperparameters have to be we have to dig deeper in there. We just started to get it to run, and yeah.
Further questions? There's one more.
Up,
just
there.
have to
And
walk through the whole hall.
Hi, thanks for the talk.
Thank you.
It may be a
Mhm.
stupid question. I don't know if it's correctly
Yes.
asked, but if your objective here is minimizing in energy, how does learning how does your algorithm compare to like a traditional like force field that just searches for the local minima, or
Yeah.
and does some kind of like perturbation to try to get into this maximum minimum energetic minimum?
So actually it's a good question. So what I showed at the beginning, that is what you're actually doing in the classical minimization, that you're just jumping immediately to the minimum. Yeah. So does that answer the question? Maybe I get it wrong.
I think the idea is that if the landscape is extremely rough,
Yeah.
so and it has a huge amount of minima, and it's also very highly dimensional. And what you typically do is either you do very slow molecular dynamic simulations that try to follow the trajectory, or you try first to do minimization to find the next confirmation. But local minimization will get you to the next minimum.
It's always depending on your start point.
Yeah,
where you're starting.
Yes.
That's where you're going down to the valley. Where you start, you're going to the next minima it can found, because that's what the gradient basically
And it's
tells
very
you.
sensitive to noise and everything. And this is supposed to robustify it if it works. Further questions? There's one more.
I just wondered if the landscape is so rough. Do you know if in nature, like the natural proteins, do they always go to the global minimum, or do they also get stuck on local minima?
And what?
In vitro, like.
Well, it can, as we saw already in the talk by Diego, it can happen that the protein is not in the configuration you need to interact with your partner, with the interaction partner. So it can happen that you have like for example, if you have a receptor that just opens up at certain things that need to be there in order to have that. Sorry.
Like when the protein folds or something,
Mhm.
does it always find the global minimum, or does it also happen that it will be stuck in a local minima and in
This
nature?
can happen.
Yeah.
Yeah, definitely.
And also one should probably mention that these energy surfaces are not really nature. This is our very, very crude approximation of nature. We forget about everything that's quantum and so on, and just pretend we can model it classically, and then that also introduces noise and so on. But
Yeah, you just model what you can actually compute.
So with
and all the
that,
rest is random.
with that, I think we're out of time, and the session is at an end. Thank you all very much for attending. Thank all the speakers again for the great talks and for staying perfectly on time, which was actually really great.
And the Julia organizing team as well. They're doing an amazing job.
So hope to see you all again on the posters, in the other talks, and on the Birds of a Feather session. Thank you.
Thank you.
Well, welcome everyone. The Health Mini Symposium officially started. Sorry for the delays. The first speaker is Alberto Baradas. He's a cognitive scientist and behavioral data analyst, and he will be talking about heart rate labs.jl, a toolkit for heartbeat time series. So when he's ready, he will come.
For the speakers, if you could always come forward 10 minutes before your starting time, that would be perfect. So we can get your mic while the other speaker is still giving it a talk. Then we save a bit of time. Thank you.
Waiting for the last 20 minutes in the other. Okay. Uh, Thank you for the introduction. My name is Alberto Barradas, as you mentioned. I'm a PhD student at TU Graz, and I've been working in cognitive science for the last 5 years. And I would like to present to you, you can see, you're able to see the slides yourself if you go to this web page. So, as I was mentioning, thank you so much for being here. I hope I can make this work from my PhD for the last years useful for the community. This is my first publication of a Julia package. So yeah, let's get started with it. I'd like to tell you a little bit about the heart rate. We're going to talk a little bit, just some small basis about what is heart rate variability, if you haven't heard of it. And we'll talk a little bit about measuring, analyzing, modeling the heart rate. When we evaluate the heart rate, how often does the heart beat? We have many different tools and techniques that can measure that. One of them is electrocardiography. You might be very used to this PQRS signal, which I'll show you in a moment. We separate from this concept and we'll tend to work with other types of signals. PPG are photoplethysmographs, or the real important time series in this case is the time series of interbeat intervals, how much time there is in between every heart rate. There exist analysis tools that help measure and evaluate these time series data. One of the most famous one is PyCardia. PyHRV is about 5 years old. It hasn't been updated. One of the best ones is included in the PyNeuroKit 2. This is already a signal that us as cognitive scientists, we tend to use a lot. Any signal that we can, any biological signal that we can measure that can help us evaluate the cognitive state of participants in our experiments, right? And there exists in Julia a package for measuring heart rate variability. This package has not been updated in 6 years, has a couple bugs. And so when I came to it, I decided to fix those bugs on a branch, and this has slowly become a lot more closer to what Cuvios is. Cuvios is the golden standard for heart rate variability analysis in science and in sports psychology. So this has been a bit of a lighthouse that we'd like to work like, right? So about the heart, everyone here hopefully has one and you have felt it beating, but there are complex processes that we can evaluate about the heart beating. We know that it beats in 2 sections, first the atrial contraction and then the ventricular contraction. And this produces different sounds that we can hear. it produces electrical signals that we most usually measure as the electrocardiogram. And it produces changes in blood pressure and many different things, right? We have an example here of the cardiac cycle. Another very common image of the cardiac cycle is also used, this one used in bicardio from the Riggles um, graph, where we can see a very important component of this, and that is the electrical activity that coordinates the heart pumping is controlled through a specific set of two nervous nodes. The vagal nerve that arrives into the heart does not directly go into the heart, but rather they have an interface with the pacemaker neurons in the heart. And this means this interface has certain characteristics, and that is exactly what we're interested in. Those characteristics produce certain filters, and neurotransmitters work at different frequencies. So there are a lot of things that we can tell about which autonomous nervous system is producing activation in the heart by knowing if the heart rate is going up or if it's going down. And as I mentioned before, you might be used to electrocardiograms like this, where you can see the PQRST. Yes, the PQRST peaks. This is not what we are working with at the heart rate lab. Because we are measuring from many different sensors, we abstract each of these beats. We don't use it, although we do measure electrocardiography with heart rate bands like this one that runners use. There are other devices like photoplethysmographs that do not produce electrocardiograms, and therefore what we use instead is the milliseconds between the heartbeats. So in the case of a photoplethysmograph, it's the milliseconds between the P and P wave in the photoplethysmograph. In the in the electrocardiogram, we use the RR peaks, and this produces a series of millisecond beats, a time series of milliseconds between beats. And it's very cheap to use, to get these devices. These are user-grade devices, which means we do not develop our own devices. We can just buy them and apply them directly into our experiments. This is very useful for getting ethics approval. And it's very useful for me as an analyst to take my analysis workflow to different labs across the world. This is very replicable science. Again, it's also very cheap and portable. You can do sports with this. So we use it a lot in sports psychology. We'll talk a little bit more about that. And the data output, it's very simple. For people here in Julia, this is a one-dimensional time series. The data itself is it's not only simple, but it's also redundant. And we'll talk about it a little bit more, because we are measuring the difference in beats between every beat. This means that the x-axis and the y-axis are somehow related. We can get the x-axis back from just the y-axis. This is the difference by adding up. This is a difference of sums. So another important thing that I'd like you to recognize is that interbeat intervals, if you change them from milliseconds, divide and get BPMs, you actually get the instantaneous beats per minute, right? This is a number that you're used to. Right now, sitting, you might be between 60 and 80 beats per minute. Right. We can evaluate this bits per minute signal by making it not instantaneous, but interpolated or evaluate characteristics from it. And this is exactly what we'll do. This is a signal that I'll demonstrate with across through the presentation. We'll see a little bit of examples about measuring heart rate variability. So when measuring, we have different domains. There are many ways of measuring heart rate variability, and we have historically many of them being useful in different areas of science. And with my work, my idea was to consolidate where is heart rate variability useful and what are these different domains telling us about the central nervous system of our participants. What can we actually tell about participants given all these different measurements? I won't go so deep right now into every measurement, But let's talk a little bit. We can measure statistic characteristics like the mean and the standard deviation. These are very common variables for for measuring heart rate variability. But we can also measure other statistics or temporal resolution, for example, the temporal discrete derivative. And model these variables as random variables that have a distribution, an empiric histogram, and extract statistics from this. Another very common thing to do, as I mentioned, is taking the sequential differential from each bit, the difference between each bit and the next, and measuring that. This is the numeric derivative. This is why it's centered at 0. And this implies the rate of change of your heart rate. If the number is positive, this means your heart is going faster. If the number is negative, your heart is slowing down. And so it can go faster by much more than 50 milliseconds, for example. And this in sports science is very characteristic. It has been described as a characteristic feature, a characteristic feature of sports performance, correlates with sport performance. Right. This is the feature that you most will see, the standard deviation of the first derivative of the heart rate interbeat interval signal. Lastly, another domain is the frequency domain, where just like electroencephalography, like EEG, we have different bands. As I mentioned, some of these bands relate to the activation of the sympathetic central nervous system, some of them with this parasympathetic central nervous system. So by modifying these parameters, we can also get to biofeedback, the feedback of your own biological signals for the regulation of your central nervous system. This is just some of the examples of the different features. Another one is the geometric domain, where you measure characteristics of the delayed differential signal. This is a Poincare plot that shows one bit versus the last one, and the last versus the one before the last one. And you have x-axis and y-axis. I'll show you an example of this one later on. Nonlinear domains are a little bit heavier and maybe more interesting for mathematical focused people. I just show an example here that we also, for an algorithm that we also use in economics, the trended fluctuational analysis that allows us to measure fractal properties of long time signals of the heart rate. These specific feature has had clinical applications. This is not so common in heart rate variability. Its use in clinical applications is relatively reduced. And with this, most of these characteristics exist in all libraries. What I want to show you right now, and what I would like to focus this conversation on, is on the heart rate lab and what can we do in Julia what can we do that Julia enables, thanks to the entire environment. First of all, at the heart rate lab, we have a lot of inputs. We can input from Elite HRV, a biofeedback training app, but we can also import from Cuvios, from text files. This is a common way of just keeping a series of integer numbers. We can also import large data sets from Physionet. This is a large open data set for open science, and a lot of heart rate databases are available here for us to compare against other populations. XDF and lab streaming layer is a protocol that allows us to communicate almost any device in the laboratory with sub-millisecond synchronization precision. So this allows us to connect many electroencephalography, oculography. All of our experiments can combine any of these devices thanks to the layer of lab streaming layer under it. We also have the widest pre-processing library of tools for pre-processing from time series, right? You can also do some pre-processing that includes electroencephalography, but this is not the case for the heart rate lab. Just from time series, we have the most flexible pre-processing library for it. And this, of course, includes very powerful data interpolations that Julia just gives us basically for free if we want to do a single interpolation. And lastly, windowed analysis. This allows us to do other type of signal analysis in the heart rate that has been described, and I just technically use it for statistical descriptions. We'll talk a little bit more about that. We mentioned the raw data. All of these slides have code. You can see the heart rate lab being used as you see these slides, especially if you have the link. I'll just show you quickly. We can detect beats that are too close or too far from each other. And the entire feature extraction is one single computational graph, which makes it very easy to optimize, to process, to model in Julia, and to memorize, to optimize certain processes, certain functions. We can go deeper into these later. I will be showing a poster presentation, which might be helpful if you have some questions in detail. Window analysis, we can take a small set, 60 bits, and slice our window 10 bits and make another analysis to extract these features. And all of these allows us to extract features of our heart rate variability through time. This is a common thing to do, for example, with spectral analysis, where we can see the change through our experiment in the frequency, the heart rate, or the breathing, even the breathing of the person that's being evaluated. And as I mentioned, the window analysis allows us to make statistical descriptions of our signals, which is very useful later on, for example, for the evaluation of normative values, which is exactly what the poster later tomorrow is about. And here comes the pretty part. Dynamical systems are free to integrate with Julia. So we can play with models like dynamic mode decomposition, which is a linearization of dynamical systems. And I've explored a couple other models that were mentioned in the 80s. They were in papers and I just brought them up. Let's take a look at them. A dynamic mode decomposition takes some specific characteristics of the signal that are linearized and then tries to reconstruct the signal. As you can see in this specific training, it works. This is one of our worst models because it forces linearization of a dynamical system. It works relatively well at short periods, and this is what matters for us, right? That we can take small windows of heart rate and model the parameters, the distinct modes within that window. So in doing so, we can also use a very common cyclical or oscillatory dynamical system and trick it into or trick our computer into believing that what we have right there is a heart rate. What we're doing is we're taking the van der Pol oscillator and selecting as the maximum point as this is where the heart decides to beat. Of course, the heart is not a van der Pol system, but this allows us to measure the parameters, the characteristics of the heart within a specific window if they were a specific model. We'll talk a little bit more about modeling. And you can also, of course, do this with the Lorentz attractor, right? You can take the maximum value and set and say, whenever we reach that maximum value, that's a heartbeat, right? In any way, all of these models, what they're trying to do is, what we're trying to do with this model is model the oscillatory nature of the heart. Of course, much better for that is an actual neuron. We can, in this case, a very simple leaky integrate and fire model can help us parameterize the activation of the sympathetic and parasympathetic system, not only as numbers, but as the actual current that is an input to the virtual neuron that is being the pacemaker, that is connecting to the pacemaker neurons in the heart, right? So this is another of the characteristics. And of course, all of these can be, leaky integrate and fires have an analytical solution, but if we have more complex models, which the heart rate lab is made to be extensible, you can integrate any model that you want and solve it with ODEs or with Bayesian inference, right? Which, of course, it can serve for parameter estimation, but also for time series analysis, right? We can predict the next 10 beats with relatively good enough accuracy. This I haven't found very useful, but of course, it's a demonstration of things that we can do with Bayesian, with Turing, with Bayesian programming. And of course, I mentioned all of these is live. What you are looking at right here is the heartbeat of a nervous presenter. What you're looking at are all the plots completely live being taken from this sensor, right? Um, as we mentioned, we have the milliseconds between every heartbeat. The differential signal is my heartbeat going up or going down. And two very specific measures: the standard deviation of the standard deviation of the signal and the standard deviation of the first derivative of the signal, or the RMSSD. The Poincaré plot, where we expect to see a specific cycle, especially in somebody who's just breathing. When you breathe in, your heart has a little bit less space, so has to beat a little bit faster to bring all that oxygen-filled blood into your bloodstream. And when you breathe out, there isn't that much oxygen in your lungs. Your heart has a little bit more space, so it actually slows down. This is a normal sinus rhythm activity, and we can evaluate that with the Poincaré plot, as well as the frequencies with which our heart is working beat to beat. Problem solving. What do we do with the heart rate lab? As I mentioned, I'm a cognitive scientist. I work on open science, and for me, it's very important that all of these technologies reachable, usable, cheap, accessible, free, and it belongs to the students, that are using and experimenting with this. So first of all, I use these material for teaching. It's very important that students learn that they shouldn't measure the two values that are highly correlated because they're dependent on each other, their functions on each other, right? So I use a lot of these online visualizations so that people get a sense of what each of the characteristics is. They can visualize it and see as they measure their own heart what happens with the actual signal. I also use this in my personal biofeedback practice. I practice a specific types of contemplative practices, and this is a very useful way of having cheap, free feedback into that. We do a lot of experiments in cognitive science, in sports psychology, in contemplation practices, and of course in cognitive science with attention, where we have been able to normalize and describe statistically not only the questions. Okay, that means 5 minutes for questions, right? Great. So let me eat a little bit of the questions. I just want to tell you a little bit about the infrastructure. We are using a heterogeneous distributed computing for evaluating the entire scientific field. I was listening to Chris Rakaka's talk today about the AI system. I'd just like to mention it if there are any questions about that. We have been able to evaluate the entire scientific field since 1950, thanks to AI and being able to make these scientific fields, maps of the scientific field that allows us to evaluate not only each feature of the heart rate variability, but their historic use in clinical and in other settings. So I invite you to take a look at the documentation and read more about the heart rate lab if you'd like to use. I'll be presenting it as a poster tomorrow at 7. Thank you so much.
Now there's a few minutes for questions.
It's very nice talk and lovely visualizations. I was curious about everything you talked about, as far as I could tell,
yes,
is about time between events.
Correct.
And you were showing the schematic earlier about what signals actually go into generating a heartbeat. I'm wondering if any things like the amplitude of any of these particular waves, if any other features other than just time between peaks have physiological relevance or are worth measuring and incorporating into any of these models, or if the time really captures enough of what you care about.
We decided for these it's not arbitrary, right? There is technical reasons why we decided to stay with this, and that is we're using a very a very diverse forms of sensors. For example, we're using millimeter wave sensors, And the point of convergence is that time series. Of course, there is a lot of value in the ECG. There is a lot of clinical value in the ECG. If you look at the electrical signal, you can actually tell if there are blocks, if there are other type of clinical things that is very useful. It's outside of the scope of the heart rate lab.
Thank you. I have a question for the specific Julia package that you present, although I can come to your poster as well. Of
course.
But to my understanding, everything that this package contains is already existing in individual other Julia packages. And speaking from experience, it's extremely difficult to maintain such a package. So as a researcher, why would I want to use this one directly instead of going at the source?
Yeah, not everything is available. As I mentioned, no other library is as complete when it comes to pre-processing. No other library has online visualization. This is not on any other software. It is difficult to maintain. I have been maintaining this for 5 years now because it's my work for the PhD. I do expect it to become, if nobody picks up or if nobody in the public would like to use this, it might slow down, as many other libraries have done. But HRV has not been updated also in several years. So these libraries are consistent. There isn't much change. What I do expect to change is exactly the bibliographic, the environment around it, right? These agenda, and this is why I wanted to mention it, the scientific environment is in constant change. Very often we find new correlations, and what we want to do is we want to move away from correlations and move into normative science, into Kuhnian normative science, where we want to start figuring out the models, not only what relates to this and what relates to that, but what are the actual models of cognition that helps us understand this field and how this moves along in the field. It's a very wide view of the study. And of course, this has also, it's not, I don't have it in the slides, but this also allows us to detect p-hacking. By doing this in a field, we can detect p-hacking and which sources of data can we trust. And most importantly, also, we can compare our data against all these PhysioNet values. This is nowhere in any other dataset. We can just import a PhysioNet dataset and compare our data directly against that. So this is not in any other.
Okay, we thank our speaker again.
Thank you so much.
So the next speaker is Aldo Giuliani, biomedical engineering and PhD student in artificial intelligence and biomedical engineering at Magna Grecia University of Cantasaro, Italy. And he will be talking about radiomics, a library for high performance radiomics feature extraction for medical images. Please welcome our Aldo.
So a moment, prepare. Sorry, one moment. I try to. Okay, so thank you to the moderator and good afternoon, everyone. My name is Aldo Giuliani. I'm an engineer and PhD student at Magna Grecia University of Catanzaro, Italy, and it's a pleasure to be here at JuliaCon 2026 to present you Radiomix JL, a new library for analysis of medical images. So, although biopsy remained the gold standard, since requests to take a smaller part of the tissue to evaluate a tumor, it is invasive, it's not feasible, and sometimes it's difficult to perform in some anatomical sites. So new approaches are necessary. One of these new emergent approach is radiomics. But what is radiomics? Radiomics convert medical images into quantitative data. So because we know the physics behind medical images, and we know that the voxel contain meaningful physical information. This approach enable a non-invasive assessment of the entire tumor to prognosis, diagnosis, and personalized treatment. So how can we transform pixels into quantitative data, structured information? The first step is image acquisition that can come from CT scan or MRI scan or PET scan. After acquisition, the tumor are segmented on his anatomical volume, and the last step provide a feature extraction. We, as you can see, extract three groups of feature. We have a first order feature that describe the distribution of intensity of the voxel, shape features that capture the geometry of the tumor. At last, we have a texture feature that capture a tumor heterogeneity. So, as just we seen, these three concepts translate operationally in 7 family of features. The first two cover shape-based and first-order statistic features. The remaining 5 formalize texture features thrown in specific matrices. For example, we have GLCM and GLRL, RLM for voxel parent sequences. We have GLSZM for 3D cluster and GTDM for local contrast. At last, we have GLDM for neighboring dependencies. So in the past, radiomics faced the reproducibility issue due to difference between algorithm software implementation. So IBSI established a standard to harmonize feature extraction, and radiomics GL is listed among reference implementation. By extracting this feature, radiomics provide the necessary quantitative information to train machine learning algorithm. And as shown in this slide, this growing potential has driven a significant increase in recent activity with an increasing number of studies focusing on the development of radiomics and machine learning based precision medicine model. At this point, a natural question arises: why Julia? The choice wasn't accidental. Julia is the best candidate for developing a library like this, given the high computational cost. Since library didn't exist in Julia, we built it ourselves. Before diving into the technical detail, I would like briefly introduce the team behind Radiomics JL, and this project is the result of a multidisciplinary collaboration between experts in engineering, physics, and medicine. Our goal is simplify the feature extraction for the user. And as you can see, we pass at the library the anatomical volume and the segmentation of the tumor, and extract radiomics feature using one single function. One of the strengths of this project is in its simplicity. The entire code base is 6,603 line of code, and it's fully modular. Each algorithm, computation algorithm, live in own module. Why this? Because we want to make the library easy to maintain and easy to extend. So other strength of the project is that we are open source, and we can see the official link of GitHub. We guarantee the interoperability with the other library, and we are registered on the general register. Other point of strength of our project is website. In fact, our website provides the necessary documentation example to facilitate the integration of Radiomic JL into different workflow. For a plug and play and PC approach, we have containerized our entire library, and as you can see, we can pull our official imager, Docker image, and you can extract directly the features from command line, mounting a local volume. One of the key of our library is flexibility across different implementation workflows. environment, sorry. And users can integrate Radiomic GL according to their specific implementation needs. And Radiomic GL has successfully passed all official IBSI data benchmarks, ensuring mathematical correctness in compliance with international research standard. And the validation set is also included in runtest.jl. In this slide, we can see the state of art of radiomics today, and although pyradiomics has historically been the reference implementation, its limited maintenance has led to home maintainers to recommend radiomics JL. Following the limitation of radiomics or of pyradiomics, sorry, the NIH Imaging Data Commons, a large archive that collect 99 terabytes of medical image is evaluating the adoption of radiomics JL. Now it's time to raise. We use pyradiomics as a reference since historically it's been a reference implementation. So in this graph we can see the execution time of radiomics JL compared with pyradiomics, and we can see how radiomic GL is faster than pyradiomics for each patient present in the dataset. We have good news from also from the cumulative time. In fact, we have reduced the median time from 1 at 36 seconds using pyradiomics to 0 at 38 seconds using radiomics JL. Radiomics JL achieved a medium speed up of 3 at 46 time compared with pyradiomics, and most patients show a 2-6 time acceleration with a maximum speed up of 13 at 9 14 time. The single case below parity was due to Git warm-up effect, and radiomics show lower execution than pyradiomics also across tumor segmentation size. The speed up reach up 14 30 at night time for smaller tumor segmentation, and increase and decrease as a tumor segmentation size increase. This slide is very important because, as you can see, we can see that each family of feature is under the IBSI tolerance reference, and this guarantee our IBSI compliance. And now we need to talk of the future implementation. We are still working to improve our library. We are working for using a GPU, and yesterday we have got good news because five family of feature are passed on GPU, and other aspect of our of the work involve the implementation of wavelet filter, so we can see a detailed analysis of BMA imaging, revealing the feature, the value that would otherwise remain invisible using a classical method. To conclude, radiomics GL guarantee the interoperability with the other library for Flux JL or MJL for deep learning and machine learning and other languages, and it average 7 times faster than Paradiomics with peak of 14 time, and we guarantee full IBSI adherence. So I leave the floor for open for your question, feedback and curiosity. Thank you all.
Now we have 3 minutes for questions. Maybe I have one question. And the GPU implementation, are you planning to use CUDA.jl like array-based programming, or are you trying to do like kernel abstraction, like kernel-based programming?
Yes, this is an important question, and thank you for a question. We are used for this first part of the work CUDA.jl.
there's a few minutes more for questions. If anyone wants to ask something. Um, yeah, maybe I'll ask another question. I work with MRI. So which type of data are you actually extracting these radiomics features from, like T1 maps, T1 weighted images, or can you explain a
Yes.
little bit more about that?
Yes, different. We are a difference between CT scan and MRI scan. The CT scan use a unfiled scale, so is standardized this approach. The features are same for CT and MRI. What change? What change? Change the type of acquisition. Maybe in at first acquisition one value say something, say one value, but in second time can say and can return other value, but the features are same for CT and MRI. Change the time and the type of acquisition. For CT, we have a standardized scale. For MRI, no. So we need to do a pre-processing of the data.
And in your group, you mainly use it for like tumor analysis, or what?
Yes, we have done a tumor. This is a MRI scans. Is a dataset from my MRI and BRATS 2021, pediatric tumors of glioma. And compared with pyradiomics, the pipeline is the same and give us the same results.
Yeah, perfect. Well, we thank our speaker again.
Okay, bye.
So the next speaker is Nicholas Hackelberg, a PhD student at Hamburg University of Technology and also a software engineer at Fraunhofer IMT. He's one of the main developers of MRI RICO, and now he will be presenting about his generic GPU accelerated framework for medical image reconstruction.
Okay. Hello, everyone. I want to tell you about how we've extended our tomographic image reconstruction packages with GPU support. And for that, I'd like to start with a small introduction to tomographic imaging. So there are many different tomographic imaging modalities available, and they usually allow us to visualize the insides of a subject without having to open them up, which of course revolutionized healthcare diagnostic and therapy. And these modalities, they often differ in the physical effect that they use to transport information to the outside. And they also differ in characteristics of the images, like the spatial and temporal resolution, sensitivity, or in the contrast. And usually we need to perform a reconstruction step on the measurement data to get the actual images. And this is especially computationally demanding process. So this is very well suited for GPU acceleration. And this process is actually mathematically quite similar for different modalities, which is why for our tomographic imaging packages MPI-RECO and MRI-RECO, we use the same reconstruction backend. So we're doing image reconstruction for magnetic particle imaging and for magnetic resonance imaging using the same mathematical core. There we've written our own Julia packages, and we are using a lot of established Julia packages like FFTV or the linear algebra package. And now the main part of my talk will be how can we extend this core with the Julia GPU ecosystem, which will then mean our ecosystem is generic across different imaging modalities, but also across different GPU backends like CUDA or AMD. And for that, let's zoom in a little bit on the reconstruction core and look at the maths behind it. Most imaging modalities you can actually formulate as a discrete linear system where you have an imaging operator A, you have your image is X, and you have some measurement and some noise data. And if we look at it from this perspective, the modalities, they just collapse into something provides us A and B, and we get out our images. And there are many different formulations of this problem. So sometimes you have a series of image if you have like multiple time series, for example, or you look at different contrasts of the same image in one problem. Regardless of the formulation, we are usually dealing with problems that are very large scale. They are ill-posed, they are noisy and often undersampled. And so it's not a question of a simple matrix inversion, but instead we need to approximate the images. And in our case, we did it with a regularized least squares approach. And in this formulation, we have a data fidelity term, and then we have one or more regularization functions. And this is exactly the way we split up our reconstruction core. So we have, on the one hand, our optimization methods and the regularization terms, and on the other hand, we have efficient implementations for the linear operators we need. And the first package we've implemented is regularized least squares, which, as the name suggests, contains our generic optimization methods. And these are specialized for the least squares approach. And then we also have a flexible toolbox for regularization terms. And one very nice thing about the iterative methods we use is that they mainly require the forward and the adjoint and the normal operation of our operator A. And so we can implement them in what's called a matrix-free fashion. So we don't need to store the elements of a matrix. We just need to implement how it acts on a vector. So that's the difference between having a matrix with all the elements implementing a Fourier transformation or calling the FFT. And to do that, we've have a collection based on the linear operators package, which just wraps established library like FFTV and makes them available as an operator. But it also has compositional operators like a product or a diagonal block matrix or a normal operator. And whenever we can, we try to have structure-aware optimization and try to retain the types so we can, for example, exploit the diagonal structure of an operator. And this is now the packages that we want to extend for GPU support. And for that, let's take a look at the Julia GPU ecosystem and derive some design constraint. Julia has first-class support for GPU programming, and usually people interact with it with a backend package like CUDA or AMD GPU. And there you get array type, you get GPU programming itself, you get library API wrappers, and you can just use normal functions, and multiple dispatch will select a GPU implementation if it's available. For us, this meant that our code would need to be compatible or generic in terms of CPU or GPU arrays. It means that all the compute data that goes into a computation has to live on the same device, and we need to preserve the backend when we perform allocations. There are two different models you can use when you do GPU programming. So you can use array programming, there the parallelism is implicit. So you use high-level functions like linear algebra, or you can do kernel programming. There you have explicit parallelism. And for us, we wanted to use as much high-level GPU compatible code as possible. And if we need to write kernels, those should really be portable across different backends. And to do that, we need to take a look at the generic infrastructure. There we have, for example, GPU arrays, which has a common array type, or we have kernel abstractions, which allows us to write kernels that are available for different backends. But we can also use things like the normal base similar function to allocate like an existing array. And this means that that we want to prefer dispatch on generic GPU array types if possible. We want to use kernel abstractions for our kernels. And overall, we want to have as much code reuse between CPU and GPU as possible to lower maintenance burden. And from those design constraints, we actually get a fairly simple rule to follow, and this is that all of our states should follow the input data. So our reconstruction packages move the measurement data to the input device, like a GPU. And then, for example, our solvers will need to derive all the state from this. And this gives us then a very nice migration checklist. We should become parametric in terms of the array type that we support, not only the element type. When we allocate temporary variables or state variables, those should be derived from an input, and we shouldn't assume CPU usage. So we should initialize with fill or with a broadcast operation. If we have CPU-specific code, we should make that more generic. And if we do have differences between CPU and GPU, we want to isolate that between small function calls and dispatch on generic GPU vectors if possible. And we can apply the same checklist, of course, also to the operator. So this is not server specific, but there it's a bit more complicated because usually they only get CPU metadata for their construction, but they need to construct and initialize GPU specific things, and they need to know how to allocate GPU arrays. And in linear operator collection, this is realized with the S keyword, which allows you to specify the backend storage type. And there we just need to pass in a GPU vector type. And then from that, we can derive everything. And usually this is enough if the backing library is GPU compatible. And if it's not, well, then we are in the case that we actually need to write our own kernels. This is what we did especially for the imaging specific kernels. And there we then just need to implement the multiplication for forward and a joint and maybe a specialized normal application of our operator. And if we've done all of these things, then once we've did that, then our backend was GPU compatible. And in the end, for our users, this meant that they now have GPU support by just loading an additional package, specifying the array type they want to use for reconstruction, and then the API overall is completely unchanged. For us as developers, this meant that we can reuse most of our code between CPU and GPU, that our GPU-specific code is very well located and isolated and doesn't require huge changes in the code base. And also the changes we needed to do, so this migration checklist, this was very mechanical and simple to do, so it wasn't a complicated change. Of course, specific imaging kernels might be quite complex, but then that's very well localize the complexity, and that's just par for the course when you want to implement such a thing. And since this approach is mostly in our reconstruction backend, this is something that we can extend and use for other imaging modalities in theory, such as CT. I've also brought some small performance snapshot back when I did this migration, like almost 2 years ago now. So this is not an exhaustive benchmark. These numbers are now just the timing average over 20 executions. For magnetic particle imaging, I compared between CPU and GPU using an CGNR solver, and there we have a speed of around 20 times. And for magnetic resonance imaging, I compared ourselves against the BART reconstruction software. And here we are a bit faster, but I would just want to stress this is not an exhaustive benchmark. So the main takeaway here should be that we are, with our approach, in the same ballpark as other MRI reconstruction software. And yeah, with these results, I'd like to thank you all for your attention. I'd like to thank all the contributors for their contributions to our packages, and I'm happy to answer any questions.
We have 3 minutes for questions. Anyone? Well, I can ask you a question. Actually, I use the underlying package, MRI Rico, a lot. I was wondering if this new framework also allows non-linear reconstruction, or can I define a non-linear operator and they're adjoint and
Yes, so in
integrate?
theory, if it fits this operator scheme, you can do it. And we also have a branch where we can kind of are more flexible in the underlying reconstruction in MRI Reco. And there we could also switch to different optimization backends and then also go to optimizations which are not regularized least square space.
Thanks for the great talk and also a very nice framework here. My question would be first on the side, is this differentiable? So if you want to drive some optimization with this framework, can we pull with an automatic differentiation the gradients or the sensitivities here?
So partially yes, but not the whole way through. So our the operators themselves, they often have defined chain rules, and the libraries underneath oftentimes as well. The solvers are at the moment very stateful, and so we can't do automatic differentiation yet, and we haven't defined chain rules ourselves. Um, we have played around a bit with, I think, Mooncake, which I think has support for a mutation, but I haven't got it to a point where it worked yet.
Thanks. And my second question would be, how flexible is the framework with respect to the sequences which are allowed? I mean, could we do like DTI sequences here or flow sequences?
So there are different layers where you can interject into this framework. So if the very high level approach, there you have kind of your pre-configured reconstructions. We have now a different approach to that where you can easily kind of inject new reconstructions to the same interface, but you can also use these solvers just on their own, and then you can construct everything yourself and do whatever reconstruction you want to do. And you can also add your own solvers to them, which then maybe have alternating iterations where they do different things. We've also done something like that for MPI.
Okay, thank you.
I was wondering what your serialization pipeline looks like, and would you be interested in the ability to directly serialize from a GPU array into some file format?
Serialization in what way?
Like, how do you save the results of your image?
Okay, so the resolve saving, this is part of the higher level packages, so MP-Areco and MA-Areco. And there, usually what we get from a reconstruction is some access array type. So it's an annotated array that you can then save. In MPI specifically, we have a custom specified data format for MPI data. But usually at the end of a reconstruction, we move back to the CPU, so we don't stay on the device.
And how does that actually get saved to disk?
It depends on the end user. So this is above the layer where the reconstruction happens, but usually it's a structured file like an HDF5.
You also use DICOM?
I'm not sure if MA-Areco has support for that, but for MPI we don't. But we can extend it, or the user could write a serialization function for that.
Okay, thanks.
Okay, we thank our speaker again, and now there's a break. It's called a coffee and cake break. I'm not sure if there's coffee or cake, but it's 15 minutes, and we start again at 3:45.
All right, then we have our next speaker, which is my co-host Carlos, and he will speak about creative ways on how to draw a Julia logo. We're looking forward to your talk, Carlos.
Perfect. Yeah, this talk could have been in recreational Julia, like, but it wasn't available this year. No. Yeah, we'll basically explain how I use the MRI machine to draw stuff, in particular the Julia logo, but this is also useful clinically, so I will explain that as well. And so in this talk, I will explain a little bit on the physics of RF excitation and how do you actually perform this like drawing. And I will also explain why is it interesting, like clinically, and potentially useful. And moreover, I will show how you can do this in a clinically feasible time, so it's useful as well. Yeah, so I will be like switching between like simple explanations and the actual like more hardcore explanation. But basically, you can imagine the spins as water droplets. When you put them in a magnetic field, they acquire like a little radio that you can talk to them at a certain frequency that is called the Larmor frequency. So you can see here in this caricature, like basically you have a tiny radio with a yellow frequency. This color will become important after, and you can communicate at that frequency and they will reply back. So the way you communicate with them is by using RF pulses. Here I'm representing it as this antenna that in blue, you see that the little like spin or water molecule has this like blue radio. And so you talk in the blue frequency and it replies in the blue frequency as well. And the thing you measure is called magnetization. You measure the magnetization of the spin, particularly the XY component of it, but yeah, that's not that important. And what really happens is that you have a magnetization vector here that is getting tipped by this blue RF pulse. That is a waveform that varies in time. The magnetization comes from this like proton of the water molecule, and due to this RF field, the magnetization gets tipped to the XY plane. So that's what we refer to as excitation. If you don't do anything, you basically will excite the whole volume. So a way you can select what part of the person to excite is basically by using spatially dependent magnetic fields. So one of them that is the most widely used is called the magnetic field gradient. So you can see here that from the top to the bottom, you basically are changing the magnetic field for each height. Each one of these water molecules have a different like color or frequency, and you can communicate to a certain frequency. So you can talk only to the yellow row. Um, this in real life looks something more like this. So you have the magnetization of the spins. You have an RF pulse that in this case is a sync RF pulse that has a certain bandwidth, and you will excite all the spins in this given bandwidth. And you can see there that you're selecting this slice. And the RF is called B1, and this magnetic field gradient is turned on at the same time as the RF pulse, and it is called GZ in this case because we're varying the magnetic field linearly in the Z direction. And this is very useful and is used all the time for slice selective excitation, and is widely used for all images that are 2D. So if you have gotten an MRI, it's probably using this, the slice selective excitation. But what most people don't know is that you can use this magnetic field gradients not only in the Z direction, but in X and Y. And suddenly you can like start exciting things in 2D. And instead of doing like slice, now what you're doing, for example, is a circle. And this is actually used clinically, believe it or not. and in cardiac MRI, this is used all the time. It's called 1D navigator or pencil beam navigator. And basically, what you have is that the heart is going up and down because of the person breathing. and we want to acquire at the same respiratory state. So what you do is that you do like a 2D excitation, and you excite a little area in between the liver and the lung, and you can see this time series, basically this time and the 1D image, and you select one small area. That's the one you will accept. This is also useful for reduced field of view acquisitions. So for example, at the left, you have an EPI sequence that it doesn't matter what it is, but it's very susceptible to off resonance. So if you acquire for a long time, you will get more off resonance accumulation. And in that image, there's supposed to be a heart, but the acquisition time is so long that it basically gets too distorted. So if you do like a reduced field of view by exciting only one region, now you corrected the resonance artifacts. Also because the acquisition window is smaller, the motion artifacts are less, acquisition time goes down, and the signal to noise ratio can go up in case of this specific acquisition. So how can we design RF pulses? Generally, what people do is for sequences or RF pulses, basically they iterate multiple times when you go to the scanner, try one, try the other, and you try n times. But I'm interested in doing this in simulation. So you can see here, ComMRI, that is my package. You can simulate different sequences in your PC and then only try the last one. So you can incorporate data. ComMRI is a package that describes these magnetic fields B that I'm referring to control the signal. And it outputs this magnetization that is what you actually measure. And this is very useful for my research because I can do like cardiac triggering, motion, and flow. And what you're actually doing is very efficiently simulating this block equation that has a component that depends on the sequence, the signal, and the tissue properties. So you can put all of these components inside an optimization problem. You can give it a target. You can optimize this RF pulse, whatever it means. And you can use as your forward operator this block simulation. And this can be set up quite nicely in a few lines of code. So you have a forward model that basically only modifies the amplitudes of these RFs. Then you simulate the magnetization you compare to the target, and that's it. For example, if you have a target for this 2D excitation, the Stanford logo, the simulation-based optimization will differentiate it, do a gradient descent, and you will get an RF pulse that at the end will excite this Stanford logo in the body. And this can be used like in a real scanner by using some of the ComMRI functions like write-seek. And thanks to Karim Farid, we were able to implement this with React and an enzyme. And what took me 4 hours, now it takes less than a second. This was done as a part of a Google Summer of Code project. And I just want to like say again that none of these figures are in the actual like water bottle or sphere. This is the pattern that the magnetization has after this RF pulse. So you have a circle, you can create a circle. If you have the Julia logo, you can generate a Julia logo, or you can create this Stanford logo that is also very complicated. Even further, you can excite the whole logo, not only the 3 circles. You can see here at the bottom the real acquired images, and you have the Coma MRI logo and the Julia logo. So just to summarize, we use Julia to write Julia using the magnetization of water spins in an MRI scanner, which is kind of cool. You can also use it for more useful stuff. So there's some problems with fat that arise in MRI. So generally, you want to suppress fat. So you can create optimized fat saturation modules, and you can see here in cardiac MRI, it's very important because all of the coronary arteries are embedded in fat. And generally, you don't want to image fat. And here you can see that you can optimize it using the same approach and get an optimized fat saturation. For other types of image, for example, EPI, that is really used for diffusion and many other like fast acquisitions, like fMRI. This is very sensitive to like off resonance and chemical shift. So if you have no fat saturation, the fat gets completely shifted and it actually starts interfering with your brain. So after doing this optimized fat saturation, basically you don't see this artifact. We can further use this for considering the patient-specific properties like of resonance. Now we have been assuming that the magnetic field is kind of perfect, but we saw in the previous talk that we actually have some deviations of the perfect magnetic field that can be described by many things, but here I'm just describing it with a V0 map. And this deviation of the ideal magnetic field distort our excitation. You can see that this Stanford logo at the top, where the of resonance is the largest, is slightly more blurry. But if you consider that in your optimization, suddenly you can get the sharpness back, which is really cool. And most importantly, with reactant and enzyme, you can do this in under a second. So you can do it in a clinically feasible time while the person is in the scanner. If this took like 10 minutes, it would be impossible to do clinically. But because it takes so little, now it's possible. We can also use simulations for MRI reconstruction. So this also like touches the previous talk, but instead of linear models, we can use a nonlinear model that instead of being a matrix, now it's called full block simulation. In particular, you have a GPU kernel that does a multi-coil MRI simulation. So you can see there that you have some receive coils, and you want to basically try to estimate this initial magnetization or proton density. But you can also estimate other properties of the body like T1, T2 maps, and you compare this instead of with this RF target with the acquired data. And if you do that, you can see at the left, that's the easiest reconstruction, sum of squares. It has aliasing because this acquisition was accelerated with an acceleration factor of 2. So basically we are violating the Nyquist theorem. That's why you get like duplicate brains. If you, for example, use MRI Reco and reconstruct the conjugate sense by using the coils, then you get a brain. But you can also get it with just using like simulations. So using a nonlinear inversion. And this takes like 4 minutes, but it's work in progress. But the cool part about it is not that you can actually get a brain, but that you can also include more stuff. So for example, you can include further imperfections of the field, of resonance, gradient impulse response functions, motion, and this is all without the knowledge of the Fourier transform. This is not using the FFT at all, just the physics. One of the main criticisms is that everything's in Julia, so some people want to use stuff on Python. So due to this Google Summer of Code project, led by Anvika Singhal. Now you can pip install CommMRI Pi, and this is a thin wrapper using JuliaCon that is able to call CommMRI, and it's also able to use GPU acceleration. Most importantly, you can change the backend, so you can use Metal, you can use CUDA or AMD. And she also added pre-compilation, so hopefully Python users will not notice the first time to do X delay that Julia is well known for. Yeah. Yeah, so in conclusion, well, this new framework that I'm developing with the MRI simulation is able to be used for RF pulse design and image reconstruction. One of the benefits of this is that you can include further properties like relaxation of resonance, V1 inhomogeneities, etc. And this compiler level GPU AD not only accelerates it from hours to seconds, but makes some of these techniques clinically feasible. And we're showing promising results designing excitation patterns and also image reconstruction. But most importantly, you can excite the Julia logo. Yes. Well, thanks for my group at Stanford. And if you have any doubts, contact me. And this is the QR for the package CommMRI that has the simulations. Yeah, thanks.
Thank you very much for your talk, Carlos. Are there any questions from the audience?
Carlos. Thanks for the great talk and also providing a great package here.
Thanks.
My question would be on the sequence design. I mean, we can do lots of fun stuff in the sequence design, but how do you ensure that the sequence ultimately can also run on the scanners?
Yeah, that's a great question. So what we're doing now is that CommMRI uses the PulseSeq format. So PulseSeq is an open source sequence format, and that way there's a few hardware restrictions that need to be satisfied. So of course, during this optimization, in this case, we're not constraining it, but for more advanced optimizations, we might be able to, or we might need to constrain, for example, the max slew rate of the gradients or the max gradient, the max V1 amplitude. All of that can be included. And then this write-seq function, what it does is that it not only writes this to a file that can be run in the scanner, but also it does checks. So if the scanner has a certain maximum that you're exceeding, it will error. So it will not let you run it or generate the file. If you go to the scanner with a file that is like basically unable to be performed in the scanner, that would not be a problem. It will fail, but it will not explode, which is nice. It will just throw that it couldn't run it. But yeah, hopefully all of these problems are caught before in this write-seq function.
Are there any other questions from the audience?
So far you talked mostly about these 2D scans, right? So 3D scans are also a thing. Is it just directly applicable here? Like, can you kind of also generate any kind of sequence in the 3D space you want and maybe optimize directly for less noise, less...
Yeah, that's a good question. Here, for example, I'm showing how most of these 2D excitations work. So you can see that you have like some type of spiral or grain that is going up. That is in 2D, but if you want to do it in 3D, you just need to add another channel. So instead of like a spiral, it will be like a weird thing with trajectory that it's 3D. But you can use it. There's some trajectories called like spins, which is kind of confusing in this context, that very quickly traverses an efficient K-space, and you can optimize an RF pulse in that to do 3D. For example, here, one thing that I didn't explain is that we're generating 2D images, but I'm doing like a 2D excitation, for example, in the heart. So how do I get the image and not like a addition of the whole body in that direction? Is because we are also having a second RF pulse that is called refocusing pulse, and that one is a slice selective. So we can do a slice selective with the refocusing pulse and this 2D excitation with the excitation pulse, and that's how we can do stuff in 3D. Thanks.
Any other questions? Then maybe I'll ask one. Are there any commercial users that you know of?
Well, this 2D excitation stuff is actually a product on the Siemens scanner. It's called like Summit, I think. So this is a technique that is used, and people sell like some packages with that. For 3D excitation, I'm not sure. But 2D excitation is definitely applied for diffusion imaging because you can reduce the field of view, and that makes it less susceptible to resonance. Yeah, so 2D is a product on the Siemens scanner at least. 3D, I'm not sure. I have only seen on research. And this other stuff that I was showing, like patient-specific RF pulse design, there are some efforts for that, but I don't think it's a product yet, but it's of interest.
But the group is not collaborating with industry partners at the moment where they have a joint project or something like that?
Well, we collaborate with Siemens directly
Ah,
for
sorry.
doing this kind of
Okay.
stuff.
Ah,
So,
okay. You are. Okay. Yeah, I understand that.
yeah, so the idea is that this is translated at some point to like the clinic, and
Mm.
now we're running it with this pulsic format. It's a little bit more research oriented more than clinically oriented, but yeah, it would be ideal if we can use this directly in the scanner. There, Julia actually give us a lot of flexibility, especially with this Julia trim. And basically, if you have a compiled version of this, you can include in this scanner C++ code, and hopefully it will work there. We'll see. There are some GPUs in the scanner that could run this optimization, but generally they're not so like strong. So we will need to try it out.
And if you would have a PhD student starting tomorrow for a year, let's say, and you don't have to write a grant, it's already the grant is sorted. What project would you give them?
That's a good question. Um, if I had a automatic grant, I will try to incorporate more stuff to this model, like for example, gradient impulse response functions, basically hardware imperfections. Right now, we are assuming that everything is kind of like ideal, but if you include more hardware imperfections, you may not only more applicable in the real world, but you can also maybe apply it for low-cost scanners that are more imperfect by design because they're cheaper. So yeah, I think that would be my next project. Try to do the hardware imperfection parts.
Where do you think the issues would arise first? Like if you basically decrease quality of input.
Well, right now what we're doing is that we have a waveform that we are assumed that is performed exactly by the scanner. That's not really the case. Like the waveform gets distorted a little bit. So whatever we optimize here will not be exactly what is being run by the scanner. So just by considering that, we can make it more accurate. There's already things like that for gradients um, called pre-emphasis. So the gradients are not exactly performed as you want, and they're pre-emphasized, so they're closer. I have not seen stuff like that for RFs uh, in conjunction with gradients, which is important for these like very sophisticated like excitations, at least.
Sorry if I missed the part, but did you basically go into that direction with like assuming noisy data or assuming sparse data, like qualitative features missing, that you test whether it is robust to that, like before going to a real, not so good machine?
Um, w- well, most of the things I try before going to the scanner are in simulation. So I do this optimization using the simulation, but you can also like simulate the whole acquisition. The optimization that I'm showing here is not using the whole acquisition or sequence. It's just using one part that is the RF pulse. So after designing the RF pulse, you put that into a sequence, and that sequence you can simulate. If the image looks fine, you probably will be fine. But yeah, how that is displayed or performed in the scanner can vary. It's not a perfect matching, so will be slightly different.
I see. Thank you very much. Okay, then we will move on to the next speaker. Let's thank our speaker again. All right, our next speaker is Kosuri. So Kosuri is a computer scientist and open source contributor to the Julia Health community. And she will speak on the very important topic of documentation accessibility for community onboarding. We're looking forward to your talk.
That's what. Hello, everyone. So thank you for joining this session of the Health Mini Symposium. And it's a pleasure to be here at the JuliaCon and also be sharing my work with you all. So my name is Kosuri Lakshmi Indu. You can call me Indu. And I'll be presenting the NUM-Focus Small Development Grant work. Yeah, and it's about improving Julia Health documentation accessibility for community onboarding. A brief introduction. I actually currently work as a specialist programmer L2 at Infosys Limited, and I've been a freshly graduated student of computer science. And my involvement with Julia Health has started with the Google Summer of Code program, wherein I've contributed to the healthbase.jl, where we have created interfaces to communicate or to connect with the OMOP CDM data. And then I've also developed a new OMOP CDM feasibility.jl package, which essentially works on understanding of how the data looks pre-cohort and post-cohort for users to understand their own data. And then I've joined this new work of NumFocus Small Development Grant, wherein I've been invited by Carlos and Jacob to work on the ecosystem improvements. And then I've served as a primary contributor for the overall Julia Health ecosystem improvements from January to April 2026. Yeah. So to get started, why was this work needed and some context on the ecosystem? So Julia Health has grown into a large ecosystem. We have 50 packages, 300 plus community members across various channels like Slack, Zulip, Discourse, and it spans across many areas like, home up CDM or observational health research, MRI simulation, geospatial health information, etc. But that growth has created three recurring challenges for us. Number one was discovery. It is a bit difficult for newcomers to also navigate through the relevant packages across the whole ecosystem. Number two was onboarding. So there were no proper end-to-end examples showing how we could interconnectedly use Julia Health. And number three was documentation, was the quality of deployment or README docs or CI varied significantly across various repositories. And as I said, discovery, onboarding, documentation, these have spanned and defined the scope of the grant. And based on this, everything that follows now is a work on solving these challenges. Yeah. So coming to the NumFocus SDG grant, goal number one was to attract new community members and contributors. And this was to do by centralizing and improving the documentation accessibility, where we wanted to have clear on RAMs for newcomers to understand tools better and also get started. Goal number two was to highlight the workflows, the end-to-end examples, and also guides on how you could, interconnect various Julia Health tools, Julia tools that can be used to apply on a real health informatics problem. And goal number three was to strengthen the community robustness, that is, to have a reproducible audit that lets us know how the ecosystem is running and to have some standards set up so that we could have several improvements across the repositories. Now, I'll be going through the goal one, two, three, and with goal number one, which is documentation. So the first tech work that was done was on the comamri.jl, where I have worked on implementing Documenter WordPress and the GPUI CI labels. So as we all know, comamri is the most active package in Julia Health, and the key deliverable of the grant was to migrate a Julia Health package from Documenter.jl to Documenter WordPress. And first, I tested it on my own package, OMOP CDM feasibility. And then we said with the same approach, me and Carlos had set up Documenter WordPress for the Coma Marai docs. And then we, fixed some batch rendering, edit issues, and path differences. Other than that, we all know that Coma Amara is a GPU simulated acceleration, and we wanted a label run system wherein the GPU CI should not run every time, and hence we modified the pipeline.yaml to so that we could get the GPUI tests so that whenever the maintainer adds on a label of running the GPUI, that's only when the GPUI CI will run, or when the whole code is merged to the main. And the rest of the time, it's again skipped so that it saves both cost of the CI and also the time. And also works for the fork PRs. So this is the example of how Documenter WordPress looks. This is the new UI of comamri.jl. And we also have a website called juliahealth.org. And as per the documentation, the goal one, a few improvements were also done on juliahealth.org in various areas. And first, CI.cd. So JuliaHealth.org is mainly a Quarto-based framework. So we built GitHub Actions pipelines, automated the GH pages deployment, added previews so that contributors could check in their how their contributions are looking without having to have it for the maintainer to run it every time. And then on the website, we added few pages, edited links, paths, and also refined the website copy. And in terms of community infrastructure, we added a health ecosystem section, which is mainly goal 3, which I'll be showing in future slides. And also the all contributors extension, which is for the maintainer to credit contributors for the work they have done. And then coming to goal number 2, which was workflows. So Julia Health, as I said, did not have onboarding or end-to-end examples throughout. So we were inspired by the work done by Flux ML Model Zoo and Agents.dl Model Example Zoo, wherein we created a curated workflow repository and we set up the whole repository, the docs deployment, initial workflow skeletons. And our 3 main workflows include patient level prediction, which includes OMOP CDM tooling, and then medical imaging, as in co-MRI, MRI, RECO, simulation, reconstruction, and the geospatial health informatics. All these, as of now, are in a very draft stage, and we plan on improving them, making them more robust. And we also look forward to committee members coming forward with new workflows so that we could add new stuff into the repository. And the same documenter.whitepress was also implemented in this, and each of the workflow has draft docs set up as of now. We plan to keep on improving this part. And coming to goal 3, this was the main ecosystem robustness goal, where our main concept was to have a reproducible audit throughout the ecosystem. And we started as a Julia Health, pipeline, wherein we linked in, took the GitHub token API key, and then we worked on, auditing all these 6 dimensions. As I mentioned, documentation, README quality, CI/CD workflow, testing, coverage adoption, structure, licensing and maturity, activity releases and engagement, issues and PR health, cross ecosystem contributor analysis, and etc. So all of these are actually run via the GitHub or actions, and then outputs are then stored in the CSV, which then get rendered, to visualizations, and the results are stored in results.md. So the first step after the audit was done was a blog post on how the current situation of Julia Health looks like, and then to also show you on how the repository looks like. This is the repository Julia Health audit, and we have data. That is, we have 3 sections here. First is results, which are the CSVs that I mentioned. We have audited 3 types of stuff, that is packages, non-packages, and contributors. We have different audit dimensions, including different aspects, features of how the whole ecosystem contains. As I said, audit packages, non-packages, and contributors. And then we have visualizations. Now, all these CSVs are then, you know, rendered and create many various types of graphs and plots are created. And then we have the history aspect, that is to look back and see how we have grown so far. We have tried to, every audit gets appended into this run summary, wherein we store all the information that each audit gives so that we could do some time series growth type of understanding on how we are at the position, how we were back then. And the same data, as I mentioned, is then rendered in the results.md, as in different types of plots, graphs and all of that with different criterias. And this is the repository that we have created. Now this gets linked to our main julia.org, and that's when the dispatch is then sent, and then the results are again updated on the Julia Health website as in the ecosystem health section, with which every first of that month this report is updated, and we have different graphs. We are talking about CI workflow, license, source, test, docs, directories, GH pages, contributing, code of conduct, and how the top 5 look like in the Julia Health ecosystem, and then various packages and what is their standing in the whole ecosystem, contributors, non-packages, and the same visualizations are rendered even here. And to show some transparency, we have the exact data linking us back to the GitHub and how it looks. And then to come back, so as I said, after the blog was done, we had planned to make this a monthly pipeline so that every month automatically this information gets updated and now shows up on the website. And this month, the latest report includes that we have 63 repositories audited, out of which 50 are packages, 13 are tools and sites. We have 97 contributors so far, 89 being people, 8 being bots, and we have totally 73 stars, 33 packages in the general registry, 271 open issues, 93 open PRs tagged, and we have good CI adoption of 86%. And so far, 265 releases have been shipped. And all of this, as I mentioned, is get refreshed automatically every month. And then, yeah, this is the same slide of how the ecosystem health looks, a few plots and graphs. And this ecosystem is reproducible. So any other ecosystem can just fork the repository, change the name of their org, have your GitHub token set, and then you are good to go. You will have the audit run for your own ecosystem. And now that the audit is done, what were those findings? So the key strengths include 86% of packages that are up CI, 98% of them have open source license, 70% provide documentation, 66 are in Julia General Registry, 265 shipped releases, and a few key improvements that we have observed are that there were less, contributing.md files or code of conduct, and contributing activity was mainly concentrated on the core maintainers who remain contributing to that specific repository, and several repositories still remain in early stages. Sorry. And yeah, so the result was having some priorities set for further improvement of the ecosystem. And now that the audit started in the month of April, and it's been 5 months of this automated monthly audit running, and few improvements include on how the packages have improved, stars have improved, and we have more human contributor, more releases, and we have closed many related issues, and the inactive tier of packages has reduced. Yeah. Now that the audit is done, we found what to do with the audit. We wanted to create some audit follow-up issues or solve those issues across the ecosystem. So we had taken the top, start 15 Julia Health repositories. Example, Neural Analyzer, Thunderbolt, Blood Flow, Trixie, CoMMRI, PubChem Crawler. And across all these, we had created targeted issues as in informational findings, and these include having set community standards, having proper project documentation, having code coverage, CI workflows, and also some actionable issues on testing and overall repository maintaining. Now, this is one such example of how the targeted issue was opened on their repositories, informing about the findings of the audit and also giving references, and also having them do the work, or maybe if it was a straightforward issues, I also would offer to help. And now that all our three goals are covered, we have ongoing and future work. Julia Health Zoo, as I mentioned, is in a very early stage, in a draft stage. We plan to improve whatever workflows that we have, that is patient level prediction in MRI, and also develop geospatial health informatics example, and also have CI as the ecosystem integration test suite, so that all these workflows automatically get tested in the integration level. And we have health-jl. This is a new dashboard that we plan to create next in the ecosystem, and some more website improvements, including feedback from the community and also any more features we want to create. And this is not part of the original grant work. Sorry. This is health-jl. It is a an interface for users to come and run the package in the user interface. And sorry, yeah, it's again a repository, and we are linking it with a dashboard where a user can, it's structured in a manner of microservices and extensions, so user can come and set up the service. And this is one simple example service we have set up. And the model package is OMOP common data model. And this, returns the structure of that table in the OMOP CDM database. And yeah, that's about it. And we have also linked the document to WordPress for this as well. And closing the session, a few acknowledgements to NumFocus for funding this work through the Small Development Grant Program. And thank you to Carlos, Jacob for the great leadership throughout the project, coordination, guidance, and strategic input. And I'm very grateful for the opportunity that was given to me and also the Julia Health community for reviewing all the PRs and also to respond to all the issues and to provide the feedback. Yep, thank you.
All right, thank you very much. Are there any questions from the audience?
Yeah, thank you. Great talk. Really excited to see the community get organized. I was interested particularly about kind of the wheat press transition and if you encountered any difficulties there. Uh,
Yeah, I mean, in the starting, we did face different path differences issues and edit links. Then we reached out to a maintainer from Documenter WordPress, and then after that, we got some understanding on how to solve them, and then we solved it. The main issues were only about the images being rendered from the repositories to the docs. That was the main issue.
and were you also thinking of using Beat for the website, the main website itself, and beyond documentation?
No, no, we haven't thought about it yet, so maybe I'll check that out as well.
Yeah, thank you.
Thank you.
Any other questions? Maybe I can ask one. We're a bit ahead of schedule. How did you get started in the community?
Yeah, my first interest started with the Google Summer of Code program, where I understood Julia Health was a growing community and we had different new packages. And then I met my mentor, Jacob, who he mentioned all the different type of work that they were doing. And then I got really interested on how the OMOP CDM, the data is and how it's getting connected, what type of work was being done. And then I started working on the patient level prediction concept. And after that, I got into the GSOC and worked on issues that we faced while doing this project and then improved, and then the grant happened.
And how was the onboarding experience for you?
I think it was quite good because Jacob, I was having direct contact with the lead of Julia Health. So I understood everything. He was always there to, resolve any issues or help in any sort of way. And the community, as in on Slack, is also very welcoming. We have developers, contributors coming in, helping each other, and it's just very good experience as an onboarder.
That's great to hear. I think we might just move on to the next session if that's okay with you. Okay, we are ahead of schedule, so we'll take a 15 minutes break and then start our time for the next next talk actually. Thank you. All right, all right. Okay, as the speakers are setting up, we're gonna get started with the last presentation of our session. I want to remind again after the session, right, for the conference picture, if you could go to the Alte Mensa, the stairs, there will be the picture taken. It would be nice to have all of you on it. So for this final talk, we will hear about the state of the Julia Health community. The two speakers that are present today are Carlos, you have heard him already, as well as Hetard. Jacob himself is unfortunately not available today, so he will not be joining live, but he sends his greetings. And with that, are you starting the presentation or he is? Okay. And with that, I hand it over to you. Thank you.
Thank you. Okay, hello everyone. Thanks for the introduction. I'm Hidayat Shah. I will be co-presenting with Carlos today. Unfortunately, Jacob couldn't make it today. So yeah, me and Carlos will be presenting on behalf of Jacob and the Julia Health community. So state of Julia Health for 2026. So basically we'll be talking about like what's new about Julia Health since 2025, JuliaCon. Uh, we will go over a little bit of the history from Julia Health. We will take a small ecosystem overview and obviously what's changed, and then what are the current project and research initiatives, also some of the future vision for the Julia Health which is planned by us. Yeah, let's. Right. So first question is why Julia Health? So modern health research right now have become more demanding, you can say. I mean, it has always needed scientific computing, but since past some years, it has acquired like it has been more demanding of performance, so it needs more high performance scientific computing. It also needs reproducibility, so you need to reproduce the same results under the same conditions. Uh, and if it's open science and community driven software, then it's like a cherry on the top, so that it's available to all of us and all of us can chime inside the health research. So this is why we like Julia Health was sort of founded or formed, because our community goals are almost same, or if not similar to that. We strive to provide a place for discussing and exploring innovation in health research, health equity as our core priority. So we want health to be equally approachable for for everyone, no matter what the situation or circumstances. Uh, Develop new research software and workflows for practical use, and we also like one of our goals is also like share all of this through either monthly meetings, blog posts, or discussions. Right. Let's move on. So today we'll be talking about all of this. I will start with a little bit of history of Julia Health. Then we will see like what the community right now is. Then we will have a very sort of brief ecosystem overview. Then we will move forward with what's changed since last year's JuliaCon. Then the current, as I said, current project and research highlights. What are some of the exciting initiatives going on right now, some works, and what we have planned in future. Okay, so to start with the history of Julia Health, it was founded by Dr. Dylan Mallett during COVID, which was around 2020. Uh, it started small, but over the year, it started getting traction. It started forming a small community around it. Then, after 2021 to 2022, it became sort of a more like it started gaining more traction, and then it was at the point where it had a growing package ecosystem. From 2022 to 2023, it developed to such a phase that we were able to join Google Summer of Code.
as an sub-organization within Julia. So yeah, after 2023 to 2024, sorry, in 2024 we had our first ever workshop in Warsaw, which is in Poland. So yeah, that was a very great milestone. And last year we had our first ever Julia Health mini symposium. If you have not seen the talks, they were really great. And we are today right now with a very nice growing international ecosystem with contributors all over the world doing fantastic work inside Julia Health, whether it's research domain or practical use of applications and everything else. So to see the community at a glance, we right now have around 300 plus community members spread across our Discourse, Slack, Zulip, and others. Obviously, they are all uh, they are from all over the world. They are international contributors. We also do monthly meetings. Recently, it has been toned down a little bit due to time zones and stuff, but we plan to again bring it back. And yeah, all the monthly meetings are also uploaded to the Julia programming language official's YouTube channel. So thanks again for that, for letting us upload to the YouTube channel. And through that medium, it also reaches to more than 100,000 people which are subscribed to the YouTube channel. Since 2023, since we have been part of Google Summer of Code, we have more than 10 successful projects or participants. So again, just a shout out to all of them and thank you to all of them. As you can see on the right, uh, from the previous talk from Indu, uh, from the ecosystem health page, this is a contributors overview. This is something nice which we have recently added. It's it shows like who is like what is the tier of a contributor, who are regular contributors or are some of the core contributors of repos or packages. Yes, for the presence, we are at Slack in the health and medicine channel, and on Zulip, we are in combined biology, health and medicine channel on YouTube. As I just said, we upload monthly meeting videos on Julia programming language. I assume there are also learnings like tutorial videos also uploaded to the Julia programming language from Julia Health. And last but not least, we are also on GitHub.org at the rate Julia Health. Now let's get on to the ecosystem overview. So Julia Health, it was the main idea behind Julia Health was not to be a one size fits all or a single framework or solution, right? So we didn't want like researchers or users to be bounded by Julia Health once they start using it. So one of the main goals was to be modular and flexible enough so that users or researchers can combine existing packages instead of reinventing solutions or reinventing new like already existing coding patterns based on the Julia Health's new opinionated options and everything. So for that, Julia Health was designed as a modular ecosystem rather than just a single software package. All the projects are existing like packages inside Julia Health. They shared as shared Julia scientific computing ecosystem also. So it's not like you can just use packages which are inside Julia Health organization. You can also use packages which are outside of the Julia Health like dataframes.jl and some other pretty fantastic nice packages. And due to that, since it is so flexible and modular, naturally new research areas also pop up within the Julia Health ecosystem. And if they reach at a phase, they can develop into their own sub ecosystems within the organization itself. And as you can see on the right, we have some of the popular packages from the Julia Health ecosystem, which are obviously Coma, MRI, Neuroanalyzer, and other packages. And some of the organizations which are a part of Julia Health or the ones which we collaborate with are BioJulia, EcoJulia, and many more. So this is the leadership structure right now. Jacob Zelko, who unfortunately isn't here right now, uh, is the Julia Health lead, and Carlos here with me is the Julia Health co-lead. And yeah, so what's changed since 2025? So last year at JuliaCon, we received quite some positive feedback regarding what we had already done up until then. But we also received some feedback saying that there needs to be more improvements to documentations and some visibility of packages and organizations which are a part of Julia Health itself, right? So we started working on it. We now have new packages and organizations page, as you can see. These list all the packages and all the organizations, also like similar companies or research labs or groups which are part of Julia Health or which collaborate with Julia Health. And yeah, then we also have ecosystem health overview, which was covered by Indu's talk, but I will again just give a brief overview. It is basically a new audit system which we have integrated, which basically what it does is it audits all the packages across the Julia health ecosystem, and it generates a summary blog or summary page which tells you the health of the ecosystem itself, so like how many open PRs are there, how many of the packages have docs, if they have docs, are they actually hosted, if they have contributing guides, if they have readmes, and many more. Both the data is also available if anyone wants to play around with it, and yeah. Uh, Another main pain point was documentation and learning resources. So documentation, like efforts to improve documentation are still ongoing. There's still a lot more to do. But yeah, obviously with the new health overview system, we now exactly know what exactly are the pain points where we should focus. So definitely, but there it's not like there's no improvement. We have added proper readmes across some of the packages. We are also trying to improve how one can contribute as a beginner or as an experienced person to Julia Health. We are also adding learning resources using Julia Health, which will have lots of blogs and everything. And finally, there are some new initiatives which will also be further covered by Carlos in future slides, one of which is the bounty program. And yeah, since last year, we also were received a NUM Focus grant. So congratulations to Julia Health for that. And with that, I will hand over to Carlos. Yeah.
Thanks. Hello. Yeah. Um, yeah, so you to say again, so we have a few organizations here that are related organizations. If you feel that you should be there, let us know because that will be important for the next point. One of the big things that we got in the last year with this non-focused small development grant, and yeah, I will explain a little bit more like how are we using that, but just a brief description of the ecosystems. I mostly work with the medical imaging, so we already had a lot of packages dedicated to input-output, like dicom.jl. We also have some visualization packages like MedEye 3D. Obviously, the package I developed for MRI simulation, MRI Rico and MPI Rico for reconstruction, and there's posterior things about segmentation. So I think in this ecosystem alone, there's a lot of modularity, and basically the packages can be like used in conjunction. Like I can simulate something with MRI, COM-MRI, reconstructed with MRI Rico, put it in a DICOM, and then segment it using one of these MedEye tools. One of the organizations that we also consider here is magnetic resonance imaging, and I'm not completely sure if there's another one that is called magnetic particle imaging. Maybe I should have included that one. So yeah, we can cover all of the whole pipeline regarding medical imaging from the acquisition to the analysis. Other ecosystems are observational health. So that's relating health metrics with geospatial information, surveys, patient level predictions. And my understanding is that Indu like worked with data sets that are involved with this. And also another part is experimental development, sequence symmetry analysis, Julia Health, LLM, toolchain. I'm not sure exactly how that is going, but it's really exciting that we're trying to couple these new technologies like LLMs for analysis of medical imaging, or sorry, medical data. and also compositional public health. Some of the research highlights are one, that there's a Julia Health related paper that has been published as a JuliaCon proceeding. So if you haven't seen it, check it out. That's basically a summary of this talk, but in a like paper version. There's other packages that had related research papers, like for example, Commemorate. But please, if you publish a paper regarding a Julia package, let us know and we can make some publicity and put this in a blog post. I'm not sure how good we'll be with that, but maybe we can automate this and make it like a recurrent blog post, like highlighting people's research. Yeah, there's also the observation health initiative. Started with health base, and we created some tutorials for getting started and blogs showing the workflows on how you can deal with this type of data in a reproducible way. So, for example, in this picture, you can see you can use Dr. Watson with Julia Health Base and to read some data set and then process that and to generate some significant um, analysis. And this basically bridged the gap between the Julia Health, Julia Stats, and some of these medical health record files. Okay, so this is the big exciting thing. So we got this non-focused small developer grant to improve Julia Health documentation accessibility for community onboarding. So some part you already saw on Indu's talk, where she showed basically about this ecosystem health and all of the documentation changes that she did across Julia Health. This was a big thing because it gave us 10K basically to develop open source further, which is really, really nice. And even Indu was sent here to Germany with some parts of the grant, which is really awesome that the open source community can self-fund that. And yeah, as I said, this is the talk of Indu. That if you didn't see it, check it out because it's really impressive what she did. Remarkably, there's again this organization health monitoring, that's CQR, that generates package summaries and also the ecosystem health metrics. For example, how many packages are doing CI, how many are using licenses, open source licenses, how many are using tests, etc. This is generated automatically with CI. And none of this is hard coded for Julia Health. You can just change the organization, and my understanding that it should run and generate this like blog post automatically with all of the figures. So this is really exciting. If someone wants to try it out, like please let us know. And yeah, I guess this is a big announcement for today. So with this non-focused small developer grant, one of the things that we wanted to do is to encourage community participation. So we decided to create a program called the Julia Health Bounty Program. So we're setting 6 found bounties, each one $750 each. How this will work if you want to scan the QR is that there's a Julia Health 2026 bounty program and package maintainers from Julia Health or related organizations. That's why I was mentioning if you want to be a related organization, let us know. So basically, if you are in that subgroup of packages, you can apply for this. The way you do it is you generate an issue in this repository. Basically, you need to describe the problem in a very focused way. And so there's a clear expected output and link to an issue in your repository. And after that, there's going to be a period where like people can contribute or volunteer themselves for the bounty. So as comments for that issue, people will say, oh, I'm very good for this because I have experience with this in this project, etc. And there are a few deadlines actually. So see if I quickly check the bounty program. Yeah, so the final deadline is to be confirmed, but basically all of the bounties needs to be resolved by then. This is because the small development grant program runs for a year, so we need to finish everything before the year ends. So the first step would be for maintainers to submit proposals, like between now actually and 1 month or something like that, September 8th. After that, people can volunteer to solve that bounty, and me and Jacob will decide the top 6, and basically those will be funded. These will be selected based on how much we think it improves the package in the community, how important it is, and also that it's achievable in this time frame. Yeah, so after that, we will need to like sort the payment methods and stuff like that, but that's basically the program. So if you're excited, just talk to me in Slack and I can help you with a few more details. Yeah, so this is open from now, so you can already apply. So if you have a very like small project that can be solved in a few months by a contributor, this is your chance. Okay. So just to like finalize the future directions, there's still a lot to be done with Julia Health regarding interoperability. There's a lot of tools in the health space that are still in Python or R, and basically for people to migrate to Julia, we will need to show how you can do X in Julia. So we're always looking for people, if they want to create a small blog post on how you can do X in Julia, that would be awesome. Also, we want to create clear on-ramps for new users, like people that are starting in Julia. Where are the packages or which packages are available? This was already tackled a little bit for by Indu. So we have a website that has all of the packages in Julia Health that are sorted in a way. Probably we need to do more that for that. We have a few PRs that need to be merged. Uh, yeah, and also like basically showcase that we can do high performance health workflows in Julia a little bit more. A few of the talks you already showed that you can improve performance just by switching to Julia. Well, it's not that easy, but you know what I mean. And yeah, always improve documentation, usability, and reliability. Yeah, so ways to get involved again, please reach out in the health and medicine Slack channel. Specifically for the bounty program, you can ask your questions there. You can start contributing. You don't need to like do anything special for that. And there's also Google Summer of Code opportunities. We have had a very good participation in the Google Summer of Code program. If you have doubts, reach Jacob Selko. He will be able to help you out with that. Yeah, thank you very much.
Thank you very much for the nice presentation. Are there any questions from the audience?
Something that is great and occurs to me is that we have several life science related kind of organizations going now between Julia Bio, Julia Pharma, and Julia Health. Do you think we need an overarching organization to coordinate between these and maybe other organizations, or how should we proceed with that?
Yeah. Do you want to answer?
Yeah, I think it's so the thing is it kind of is similar. I don't know if you know XKCD comic. He has a comic says that okay, we have 14 standards. Let's make a standard which is another standard to maintain this 14 standards, and now you have 15 standards kind of thing. Uh, it is definitely possible, but I think it will just increase the friction. So they one thing I would suggest is they should all have a group or kind of place where they can freely suggest ideas, not just like an structure which does stuff and which are all of this sub organizations are part of, right? Yeah, I think that should answer the question hopefully.
Yeah, just to add to that one, I think we definitely have some synergies between these adjacent organizations. Um, if if we need a super organization, that's to be seen. But I think what we definitely need to do is start like talking to each other. The first step is the Birds of a Feather happening this Friday. Free ad. So please join.
Yeah, thanks for that advertisement. Definitely join. I think sort of following on that, I would like to join together because I want your guys' energy in helping with BioJulia because I think Jacob and you all have done a great job of sort of promoting and building these structures that in BioJulia we've been much more sort of loosey goosey and don't have much structure. And so, I guess my question is, do you think there is, I guess, how to phrase this? What are like the earliest steps or what are the most important things to sort of start with building up the community? Because right now, we have this birds of a feather. The hope is to sort of kick off a little bit more organization and community building. But like if you had to pick two or three things, 'cause we're all, busy people and can only focus on so many things, what would be the two or three like highest impact things that you guys think are important for developing this community and keeping it going and keeping interest going?
Yeah, that would be a fantastic question for Jacob because basically he he started it all.
Yeah.
I think he has like a lot of energy and he was able to build a community and I just joined. So I didn't do the heavy lifting, but definitely what I think people appreciate is seeing activity. So like if they see that some things are going on, they will get excited and contribute. Um,
One thing I would like to add is so when I first joined the community, right, Julia Health was like in his initial stages, right? So what I personally liked was first of all, yeah, as he said, it was so there were people who wanted it to be more active and they were regularly trying to make that possible. Another thing was they were very reachable in the sense that they had a, let's say, old website, right, but still you can just navigate around it. You can you as a new user, where you can reach out to the interested people or the community itself, right? So that should be the first step. And second step is the person or the people who have helped uh, building the community or who are helping building the community. And this is personally which I liked was Jacob regularly did shout outs to them. So in monthly meetings or on the Slack channels and everything. So the people contributing feel appreciated. So and seeing them, others also get motivated, right? So naturally, that will just yeah tumble down. I hope that answers your question. Thank you.
I think also like the presentation that you did, right? Formalizing the process a little bit, having measurable, trackable pieces like every month, like having something like that, someone like that. Look at this organization and you're like, what can we make better? And like, I think this to me also really stands out in your ecosystem and the way the organization is running, that gives the whole thing a good shape. Are there any other questions?
just a small comment about that again. Like this fork, sorry, this package that does the audit, you can just fork it and change your organization, and the audit will be generated for your organization. The blog post thing is slightly more complicated because some data needs to be transferred to like some documentation page, but at least the JSON with the raw data can be generated automatically.
Thanks for sharing that. I think that's really nice that we keep it open source and everyone can reuse it also. Any final remarks, questions of anyone? Okay, then, I mean, once again, the shout out to the BOF session. This is exactly the type of topic we want to discuss. We've got hosts from all three sessions here now as well. So please all feel invited, even though the title is still the biology one. And with that, I think we're going to close this session. Thank you very much all for attending. Thanks to the speakers. And I wish you a wonderful rest of the conference. And reminder for the picture again.